Subscribe so you don't miss out on any of these videos. The universe is a vast, mysterious place, filled with celestial oddities that challenge our understanding of physics, planetary formation, and the very nature of reality itself. Among the countless enigmas scattered across the cosmos, one of the most baffling discoveries in exoplanet research is the existence of planets that orbit backward, defying the natural order we expect from planetary motion. In a universe governed by gravity and angular momentum, these so-called retrograde planets are anomalies that raise profound questions about the chaotic forces at play in planetary formation. How do these planets end up moving in a direction opposite to their star's rotation? What mechanisms could allow such a strange orbit to exist? And what do these backward-moving worlds tell us about the deeper mysteries of space? The answers to these questions challenge our conventional models of planetary evolution and force us to reconsider what we thought we knew about how solar systems form and evolve over time. To understand why a backward-orbiting planet is so strange, we first have to examine how planetary systems typically form. The birth of a planetary system is a process deeply tied to the birth of its star. When a star begins to form, it does so from a massive cloud of dust and gas collapsing under gravity. As the cloud condenses, it begins to spin, creating a flattened disk of material around the newborn star. This disk, known as a protoplanetary disk, contains all the building blocks needed to form planets. Crucially, because the disk is rotating in the same direction as the collapsing cloud, the planets that form within it naturally inherit this motion. This is why in our own solar system, all of the planets orbit in the same direction as the Sun's rotation. This is simply the expected outcome of the fundamental laws of physics governing planetary formation. But what happens when a planet defies this natural order and orbits in the opposite direction? This is the mystery of retrograde exoplanets. Planets that orbit their host stars in the wrong direction, seemingly violating the very principles that govern planetary motion. The existence of such planets is not just a minor oddity. It is a direct challenge to our understanding of how planetary systems evolve. How could a world end up moving against the natural spin of its system? What forces are at play that could override the dominant direction set by the star's formation? These questions have fascinated astronomers and led to a series of theories attempting to explain the seemingly impossible. One possible explanation for the existence of retrograde planets involves violent gravitational interactions. In a young planetary system, worlds do not form in perfect harmony. There are chaotic gravitational forces at play, with planets tugging on one another, competing for stable orbits. In some cases, a planet might experience a gravitational kick from another planet, sending it into a highly eccentric orbit that loops far from its star before falling back inward. If this gravitational chaos is extreme enough, it can lead to a complete reversal of the planet's orbit. This process, known as a planet-planet scattering event, is one of the leading theories for how a world might end up moving in the opposite direction of its star's rotation. Another explanation involves interactions with a distant stellar companion. Many stars exist in binary or multi-star systems, meaning they have a gravitationally bound companion star orbiting nearby. If an exoplanet exists in such a system, the gravitational influence of the companion star can disrupt the planet's orbit over millions or even billions of years. This process, known as the correlative mechanism, can cause a planet's orbit to become highly tilted or even completely flipped, resulting in retrograde motion. This mechanism has been observed in exoplanetary systems and provides a compelling explanation for some of the backward-orbiting worlds that astronomers have discovered. There is also the possibility that a retrograde planet did not originate within its current system at all. Instead, it may have been captured from another star system entirely. The universe is a chaotic place, and stars do not remain stationary. Over millions of years, they drift through the galaxy, sometimes passing close to one another. During these encounters, it is possible for a planet to be stolen from one star and captured by another. If this happens at just the right angle, the captured planet may end up in a retrograde orbit around its new host star. While this scenario is less common than the other theories, it is still a plausible explanation for some of the most extreme retrograde planets we have discovered. One of the most famous retrograde exoplanets is WASP-17b, a gas giant located about 1,300 light-years from Earth. This planet was one of the first to be confirmed to have a backward orbit, and its discovery sent shockwaves through the astronomical community. WASP-17b is an enormous planet, nearly twice the size of Jupiter, yet it defies conventional planetary formation models by moving in the opposite direction of its star's rotation. Theories suggest that a past gravitational interaction, possibly with another massive planet, could have flipped its orbit, or it may have been influenced by a nearby passing star. Whatever the cause, WASP-17b remains a prime example of the strange and unpredictable nature of the universe. Another fascinating case is HAT-P7b, a hot Jupiter that also exhibits retrograde motion. This planet orbits extremely close to its star, suggesting that whatever process caused its backward motion must have been highly dramatic. Some scientists believe that HAT-P7b once had a neighboring planet that was ejected from the system, leaving it in its current unusual orbit. The presence of a distant companion star further complicates the story, as its gravitational influence could have played a role in altering the planet's trajectory over time. The existence of retrograde exoplanets raises profound questions about the nature of planetary formation and the forces that shape solar systems. If planets can be flipped, scattered, or captured so easily, it suggests that planetary systems are far more dynamic and chaotic than we once thought. It also means that our own solar system, which appears relatively stable and orderly, may not be the cosmic norm but rather an exception. Understanding these strange worlds is not just an academic exercise, it has implications for our search for habitable planets and extraterrestrial life. If planetary orbits can be altered so drastically, then the conditions necessary for life may be more fragile than we realize. A planet that undergoes a dramatic shift in orbit could experience extreme climate changes, making it inhospitable for life as we know it. At the same time, the discovery of retrograde planets also expands our understanding of what is possible in planetary science, pushing the boundaries of our knowledge and opening new avenues for research. As astronomers continue to discover more exoplanets, the number of known retrograde planets is likely to grow. Future space telescopes, such as the James Webb Space Telescope and upcoming exoplanet missions, will allow scientists to study these worlds in greater detail, unlocking new insights into their origins and the forces that shape them. The story of retrograde planets is still being written, and each new discovery brings us closer to understanding the full complexity of planetary systems across the universe. The existence of planets that orbit backwards serves as a reminder that the universe is full of surprises. Just when we think we have figured out the rules that govern the cosmos, we find something that challenges our assumptions and forces us to think in new ways. Retrograde planets are more than just a curiosity, they are a testament to the endless complexity of the universe and a glimpse into the vast, untamed forces that shape the cosmos. The more we learn about these strange worlds, the more we realize just how little we truly understand about the nature of planetary formation and the chaotic beauty of the universe itself. The discovery of retrograde exoplanets not only reshapes our understanding of planetary motion but also forces us to rethink how stable and predictable planetary systems truly are. While our solar system appears well-ordered, with planets neatly aligned in the direction of the Sun's rotation, the growing number of backward-orbiting worlds suggests that chaos is far more common than we once believed. This raises a fundamental question. Could a planet in our own solar system have once moved in a retrograde orbit, or could one still exist undiscovered in the outer reaches of our system? To explore this idea, we must first consider the Kuiper Belt and the Oort cloud, regions of our solar system filled with icy bodies and dwarf planets. These distant realms are home to some of the most unusual objects in our solar neighborhood, and some of them exhibit highly eccentric orbits. If a planet-sized body were to be discovered in the Oort cloud with a retrograde orbit, it would provide compelling evidence that planetary systems can experience extreme orbital disruptions over time. Some scientists even speculate that a hypothetical Planet 9, an as yet undiscovered world thought to exist beyond Neptune, could have an unusual orbit influenced by gravitational interactions in the past. If such a planet were found to have a retrograde motion, it would radically change our perception of the history and evolution of our own solar system. But beyond our solar system, the case for retrograde planets grows even stranger. Some scientists have proposed that there may be entire planetary systems where retrograde motion is the rule rather than the exception. If a star system formed in a particularly chaotic environment, perhaps in a densely packed star cluster, then the interactions between forming planets, neighboring stars, and interstellar debris could be so extreme that multiple planets could end up in retrograde orbits. This would create a solar system that looks nothing like our own, with planets crisscrossing in bizarre, seemingly unpredictable patterns. The discovery of such a system would completely overturn our understanding of planetary evolution, proving that the normal model we use to describe planetary formation is just one of many possibilities. One of the most fascinating aspects of retrograde planets is the impact they have on their host stars. When a planet orbits in the opposite direction of a star's rotation, it creates unique gravitational interactions that can cause the star to wobble in unusual ways. This wobbling effect, known as the Rossiter-McLaughlin effect, is one of the primary ways astronomers confirm that a planet is in a retrograde orbit. As telescopes become more advanced, scientists are using this technique to identify more and more of these strange worlds, revealing that they are not just rare outliers but a significant and unexpected part of planetary science. Another intriguing possibility is that some retrograde planets might not have been born as planets at all. Instead, they could have started as rogue planets, planets that formed in one star system but were ejected due to gravitational instabilities. These wandering planets drift through space, sometimes for billions of years, until they are captured by a new star. If a rogue planet were captured at just the right angle, it could settle into a retrograde orbit around its new host star. This scenario suggests that some of the planets we observe today may have originated in entirely different solar systems, making them cosmic nomads that have journeyed across the galaxy. The implications of retrograde planets extend beyond just planetary formation. They also challenge our understanding of the conditions required for life. Most habitable planet models assume stable, circular orbits where temperatures remain relatively consistent. However, if a planet's orbit has been dramatically altered, whether by planet-planet scattering, gravitational tugs from a companion star, or an ancient collision, it could experience extreme climate variations. A world that once had liquid water could freeze over or become a boiling wasteland due to these changes. On the other hand, a planet that was initially too cold for life could, through gravitational disturbances, be thrown into a new orbit where conditions suddenly become more favorable. This raises the fascinating possibility that life could emerge in places we never expected, on planets that have undergone chaotic transformations. Another astonishing aspect of retrograde planets is how they influence our search for extraterrestrial life. When astronomers look for potentially habitable exoplanets, they often focus on Earth-like worlds with stable, prograde orbits. However, if retrograde planets can exist in habitable zones, it means that life could be found in much stranger environments than we once believed. Could an alien civilization exist on a world that orbits its star backward? Could advanced lifeforms have adapted to the unique conditions created by such an unusual orbital configuration? These questions push the boundaries of astrobiology, forcing us to expand our definitions of habitability and reconsider the criteria we use when searching for extraterrestrial civilizations. As technology advances, new missions and telescopes will help us unravel the mystery of retrograde planets. The James Webb Space Telescope is already providing unprecedented insights into exoplanet atmospheres, allowing scientists to analyze the chemical compositions of these distant worlds. Future space observatories, such as the European Space Agency's Plato mission and NASA's proposed Habitable Worlds Observatory, will likely uncover even more retrograde planets and provide deeper insights into how they form. With each new discovery, we come closer to answering some of the most fundamental questions about planetary formation and the chaotic forces that shape the universe. The existence of retrograde planets is a testament to the incredible variety and complexity of planetary systems. They remind us that the universe does not always follow simple, predictable rules. Sometimes, the cosmos surprises us with phenomena that seem to defy logic. While our solar system may appear orderly and structured, the broader universe is a place of wild dynamism, where planets can be flipped, scattered, or captured in ways we never expected. Ultimately, the study of retrograde planets is not just about understanding strange orbits. It is about uncovering the deeper mechanisms that govern the formation and evolution of worlds. It is about recognizing that the universe is a place of constant change, where even the most fundamental rules can be rewritten by powerful cosmic forces. As we continue to explore and discover, retrograde planets will remain one of the most intriguing puzzles in astronomy, a puzzle that challenges our assumptions and expands our understanding of the cosmos. And perhaps, one day, we may even find a retrograde planet that defies expectations in an even greater way, one that harbors life, intelligence, or something beyond our wildest imagination. Until then, the search continues, and with every new exoplanet discovery, we come one step closer to understanding the full, bewildering complexity of the universe. The concept of retrograde planets extends beyond simple orbital mechanics. It fundamentally challenges the way we understand planetary systems and their long-term stability. When we observe planets orbiting backward, we are witnessing the remnants of chaotic past events, cosmic battles between gravity and inertia that have reshaped entire solar systems. But this raises a profound question. If these disruptions are so common in the universe, how rare is our own solar system's relative stability? One of the biggest mysteries tied to retrograde planets is the role of giant planets in shaping their orbits. In many cases, astronomers suspect that massive gas giants are the culprits behind these gravitational disruptions. When multiple large planets exist in a system, they can enter periods of gravitational resonance, where their orbits exert powerful influences on one another. These interactions can eject smaller planets into deep space, pull them into highly eccentric orbits, or, in some cases, completely flip their trajectories, forcing them into retrograde motion. Consider a system with a hot Jupiter, a massive gas giant that orbits extremely close to its star. These planets are often found in unexpected locations, much closer to their stars than traditional planetary formation models would predict. Many of these hot Jupiters have retrograde orbits, leading scientists to suspect that they migrated inward from their original locations through interactions with other planets, or even companion stars. This inward migration process may also be responsible for flinging smaller planets into unusual orbits, including retrograde paths. The presence of a binary star system can also play a significant role in the development of retrograde planets. Some exoplanets orbit not one, but two stars, caught in a delicate gravitational dance between both stellar bodies. If one of these stars has a strong gravitational influence, it can pull a planet's orbit in unexpected directions over long periods, leading to extreme orbital tilts or even complete reversals. These interactions, known as the correlative mechanism, can take millions or even billions of years to fully develop, demonstrating that planetary systems are constantly evolving in ways we are only beginning to understand. Interestingly, the existence of retrograde planets also raises questions about the fate of our own solar system. While our planets currently orbit in an orderly, prograde fashion, that stability is not guaranteed forever. Over billions of years, gravitational interactions, passing stars, and even the slow drift of the Sun itself through the galaxy could alter the delicate balance of planetary motion. Some models suggest that in the distant future, Mercury could be ejected from the solar system, or even crash into the Sun. If a massive perturbation were to occur, such as a close encounter with a rogue star, it is entirely possible that one or more of our planets could be forced into a retrograde orbit, fundamentally altering the structure of our solar system. Another compelling aspect of retrograde planets is how they challenge the way we search for exoplanets in general. Traditional planet hunting methods, such as the transit method and radial velocity method, are designed with prograde planets in mind. When a planet orbits in the opposite direction of its star's rotation, it can create misleading signals that make detection more difficult. This suggests that we may have only discovered a fraction of the retrograde planets that exist, simply because our detection methods have not been optimized to find them. Future advancements in exoplanet discovery techniques, including direct imaging and improved spectroscopic analysis, may reveal an even greater number of these backward-moving worlds. Retrograde planets also pose fascinating questions about planetary atmospheres and climates. A planet's orbit affects everything about its environment, from the length of its seasons to the way its weather systems develop. If a retrograde planet also has an extreme axial tilt, it could experience climate patterns unlike anything seen on Earth. Some scientists speculate that such planets could have chaotic weather systems, where extreme storms, unpredictable temperature shifts, and irregular day-night cycles create conditions that challenge even the most resilient forms of life. But despite these challenges, retrograde planets may still be capable of supporting life. Some planetary models suggest that a retrograde orbit does not necessarily prevent habitability, especially if the planet is located in its star's habitable zone, the region where liquid water can exist. In some cases, a planet's backward motion could even create unique conditions that foster the development of life. For example, if a retrograde planet experiences prolonged periods of daylight and darkness due to its orbit, it could lead to the evolution of organisms that thrive in extreme environments, similar to deep-sea creatures on Earth that have adapted to darkness and high pressure. Perhaps one of the most mind-bending ideas regarding retrograde planets is their potential connection to extraterrestrial intelligence. If we consider that these planets form through highly unusual and chaotic processes, it is possible that any life that evolves on them would develop under very different conditions from life on Earth. Could alien civilizations exist on worlds where the rules of planetary motion are completely different from what we consider normal? Could intelligent beings on a retrograde planet develop a unique understanding of physics, time, and celestial mechanics due to their planet's bizarre motion? Even more intriguingly, if an advanced extraterrestrial civilization had the ability to manipulate planetary orbits, perhaps through the use of megastructures or gravitational engineering, it could theoretically force a planet into a retrograde orbit intentionally. Such a civilization might have motivations beyond our comprehension, but the presence of an artificially placed retrograde planet would be a strong indicator of advanced intelligence. Some scientists have even speculated that unusual planetary movements could be a potential technosignature, an observable clue that intelligent life exists elsewhere in the cosmos. The study of retrograde planets is still in its infancy, but it is rapidly becoming one of the most exciting fields in astronomy. As we continue to discover more of these backward-moving worlds, we are forced to reconsider our fundamental assumptions about planetary formation, stability, and the very nature of the universe. With each new exoplanet discovery, we peel back another layer of the cosmic mystery, revealing that the universe is far stranger and more unpredictable than we ever imagined. Ultimately, retrograde planets serve as a reminder that the universe does not always follow simple rules. Just when we think we have a clear understanding of how planets form and behave, nature surprises us with something completely unexpected. These bizarre, backward-moving worlds are not just anomalies. They are windows into the deep, chaotic history of planetary systems, offering us valuable clues about how worlds evolve, collide, and transform over time. And as our telescopes and space missions grow more advanced, we may one day find an exoplanet so strange, so utterly unlike anything we have seen before, that it forces us to rewrite the very foundations of planetary science. Perhaps that planet will be a retrograde world, orbiting its star in complete defiance of everything we thought we knew. Until then, the mystery continues. The study of retrograde planets is not just about understanding how these worlds came to be. It is about pushing the limits of our understanding of celestial mechanics, planetary evolution, and the dynamic chaos that governs the universe. Every time we discover an exoplanet that defies our expectations, we are reminded that the universe is a place of infinite complexity, filled with mechanisms and forces that we have only begun to comprehend. One of the most pressing questions surrounding retrograde planets is whether their formation and evolution are common or rare occurrences. When astronomers first began discovering these worlds, they were thought to be anomalies, outliers in an otherwise orderly universe. But as more exoplanets have been detected, retrograde orbits have turned out to be more frequent than initially expected. This suggests that the processes responsible for these peculiar orbits may be more fundamental to planetary formation than we once believed. Consider the fact that in our own solar system, planetary orbits are relatively stable, following the retrograde motion of the Sun's rotation. This was long thought to be the natural result of planetary formation, a process in which a rotating disk of gas and dust collapses under gravity, forming planets that inherit the motion of their parent star. The discovery of retrograde exoplanets challenges this classical model, suggesting that planetary orbits can be far more dynamic and unstable than once assumed. One hypothesis is that many planetary systems begin with all their planets in prograde motion, but over time, gravitational interactions between large bodies, such as gas giants, or even rogue planets passing through, can dramatically alter the orbits of smaller worlds. Some planets may be pulled into eccentric orbits, while others may be flipped entirely, causing them to move backward in relation to their star's spin. This type of gravitational upheaval could be a fundamental phase in the life cycle of many planetary systems, meaning that retrograde planets are not rare exceptions but rather an expected outcome in many cases. The role of stellar companions in shaping planetary orbits is another key factor. Many stars exist in binary systems, where two stars orbit each other in a gravitational dance. When planets exist in these systems, their orbits can become highly unstable due to the competing gravitational forces from both stars. This instability can lead to extreme orbital inclinations, including the possibility of full retrograde motion. The correlative mechanism, a gravitational effect that occurs in triple-body systems, is a well-known process that can drive a planet's orbit into a retrograde state over millions of years. Interestingly, there is also speculation that entire planetary systems can be flipped by external forces. If a young planetary system forms in a dense stellar environment, such as a globular cluster or a region with frequent supernova explosions, the gravitational influence of passing stars or shockwaves from stellar deaths could alter the angular momentum of an entire system. This means that some planetary systems may have formed in prograde motion but later experienced a large-scale event that forced all their planets into retrograde orbits. If true, this would imply that retrograde planetary systems might be more common in regions of the galaxy with high stellar densities. Beyond the mechanics of how these planets form, there is the question of what they can tell us about the past history of their respective solar systems. Retrograde planets are not just curiosities. They are clues to the violent events that have shaped their existence. Every retrograde orbit is evidence of a cataclysmic event in the past, a collision, a near-miss with another celestial body, or a massive gravitational upheaval that changed the course of planetary evolution. In this sense, studying these planets is like being an interstellar archaeologist, uncovering the hidden history of distant worlds. The implications of retrograde planets extend beyond planetary science and into astrobiology, the study of life in the universe. Could life exist on a retrograde planet? And if so, how would it differ from life on Earth? At first glance, retrograde motion might not seem like a major factor in habitability. If a planet orbits its star at the right distance, has an atmosphere, and possesses liquid water, it could theoretically support life. However, the orbital dynamics of a retrograde planet could introduce unique challenges for potential life forms. For example, a retrograde orbit often results in significant climate instability. If a planet has an extreme tilt or an eccentric orbit, it may experience unpredictable seasonal changes, with prolonged periods of extreme heat followed by deep freezes. These conditions could make it difficult for life to develop in stable environments. However, on Earth, life has proven to be extraordinarily adaptable, with extremophiles thriving in deep ocean trenches, frozen tundras, and even highly acidic environments. If similar life forms exist elsewhere in the universe, they might be capable of surviving even on the most chaotic retrograde worlds. Another fascinating possibility is how intelligent civilizations might interpret their own retrograde world. On Earth, our understanding of physics and planetary motion is shaped by the fact that our planet orbits the Sun in a prograde direction. But imagine a civilization developing on a planet that moves in the opposite direction of its star's spin. Would they perceive time differently? Would their early astronomical models have struggled to explain why their world behaved so strangely? If such civilizations exist, their perspective on the cosmos might be fundamentally different from our own. In some ways, the discovery of retrograde planets is a humbling reminder that our own solar system is not the standard model of how planetary systems form. Instead, it appears that nature is far more creative, producing an incredible diversity of planetary architectures, some of which defy our expectations entirely. As telescopes become more advanced, including future space-based observatories like the James Webb Space Telescope and next-generation exoplanet missions, we will gain even more insight into the nature of retrograde planets. These new tools will allow us to analyze their atmospheres, study their compositions, and perhaps even detect signs of habitability, or life itself. If we were to find a retrograde exoplanet with clear indications of biological activity, it would force us to reconsider many of our assumptions about the conditions necessary for life. It would suggest that even in the most turbulent and chaotic environments, life can find a way to survive and evolve. But beyond scientific implications, retrograde planets capture our imagination because they challenge our understanding of order in the universe. We often assume that celestial bodies should move in predictable ways, following the natural flow of gravity and angular momentum. Yet these backward-moving worlds remind us that the cosmos is full of surprises, governed by laws that sometimes lead to outcomes that seem counterintuitive. The existence of retrograde planets is a testament to the universe's unpredictability. They serve as cosmic anomalies, pushing us to question how planetary systems evolve, what forces shape them, and whether life can arise in the most unexpected places. They remind us that the universe is far stranger and more complex than we can imagine, and that every new discovery has the potential to rewrite everything we thought we knew about the cosmos. As we continue to study these enigmatic worlds, one thing is certain: the mystery of retrograde planets is only just beginning to unfold. With each new exoplanet discovery, we take another step closer to understanding the grand, chaotic dance of the universe, one that often moves in ways we never expected. The mystery of retrograde planets is far from being solved, and with every new discovery, our understanding of planetary formation and evolution continues to evolve. These strange, backward-orbiting worlds challenge our fundamental assumptions about how solar systems should behave, forcing astronomers to rethink the standard models of planetary dynamics. The more we study them, the more we realize that the universe is not a neatly ordered place but a chaotic, ever-changing system where strange and unpredictable phenomena are not just possible but common. One of the most intriguing aspects of retrograde planets is their potential role in the grander cosmic narrative. If these planets are evidence of past cataclysmic events, whether through violent gravitational interactions, planetary migration, or even stellar disruptions, then they serve as cosmic records of the turbulent history of their solar systems. Understanding how and why they exist helps us reconstruct the past, allowing us to piece together the dramatic forces that have shaped planetary evolution across the galaxy. But beyond their formation and physical characteristics, one of the biggest open questions is whether retrograde planets can sustain life. While the challenges of such worlds, unstable orbits, extreme seasons, and potential atmospheric disruptions, might seem to make life less likely, we cannot rule it out. Life on Earth has demonstrated an extraordinary ability to adapt to extreme conditions, and if biology can emerge in the harshest environments here, it is conceivable that alien life could thrive on a retrograde planet despite its apparent challenges. The very nature of habitability itself is being redefined as we continue to study exoplanets. Traditionally, astronomers have focused on the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist. However, we now know that many factors contribute to habitability beyond just distance from a star. The composition of a planet's atmosphere, its magnetic field, and even its orbital characteristics can all influence whether life can develop. In this sense, retrograde planets may not be as inhospitable as they seem. Imagine a retrograde exoplanet with a thick atmosphere capable of regulating temperature despite its erratic orbit. If such a planet had a large ocean, it could provide a stable environment for life beneath the surface, even if the conditions on land were extreme. Deep-sea hydrothermal vents on Earth have already shown that life can thrive in complete darkness, relying on chemical energy rather than sunlight. If similar conditions exist elsewhere, retrograde planets might not just be habitable but could even host thriving ecosystems. The search for life beyond Earth has always been driven by the idea that the more we understand extreme environments, the better we can predict where life might exist in the universe. Retrograde planets represent an extreme case, but they also expand our definition of what is possible. If life can emerge on a world that defies our traditional understanding of planetary motion, then it could exist in countless other unexpected places throughout the cosmos. Beyond habitability, retrograde planets also raise fascinating questions about how intelligent civilizations might perceive the universe. If an advanced alien species evolved on a retrograde planet, their entire understanding of planetary motion and astronomy might be different from ours. Would they have developed different models of celestial mechanics? Would their perception of time and motion be altered by their world's unusual orbit? It is intriguing to consider how different the intellectual and scientific history of such a civilization might be compared to our own. As telescopes become more advanced and we continue to refine our methods of detecting and analyzing exoplanets, we will likely uncover even more retrograde worlds. Some of them may turn out to be habitable, and some may offer entirely new insights into planetary formation and the role of gravitational interactions in shaping solar systems. But one thing is certain: every retrograde planet we discover adds another layer to the mystery of the universe, reminding us that even the most fundamental laws of physics can sometimes lead to unexpected and astonishing outcomes. The study of retrograde planets is not just about understanding how they formed or why they exist. It is about expanding our perspective on the vast and unpredictable cosmos we inhabit. It is about recognizing that the universe is a place of endless surprises, where even the most counterintuitive phenomena can turn out to be common. And ultimately, it is about the thrill of discovery, the realization that no matter how much we think we understand, there is always more to learn, more mysteries to uncover, and more wonders waiting to be explored. The mystery of retrograde planets continues to challenge our understanding of celestial mechanics and planetary evolution. These enigmatic worlds, defying the conventional motion expected of planetary systems, serve as testaments to the chaotic and often violent processes that shape the universe. Each new discovery of a retrograde exoplanet is like uncovering a cosmic puzzle piece, offering insights into the forces that govern planetary migration, star-planet interactions, and even the potential for habitability in extreme conditions. One of the most pressing questions that retrograde planets pose is whether their unusual orbits are the result of gradual processes over millions of years or sudden, catastrophic events. In some cases, it appears that slow gravitational influences, such as those exerted by a distant stellar companion, can warp orbits over vast timescales, gradually shifting a planet's trajectory until it moves in the opposite direction of its star's rotation. This slow transformation is supported by the correlative mechanism, a process in which a distant gravitational force causes a planet's orbit to become highly eccentric and eventually flip entirely. But other retrograde planets seem to have experienced much more sudden and violent disruptions. In some planetary systems, gravitational interactions between gas giants, known as planet-planet scattering, can lead to extreme changes in orbital paths. If a planet is ejected from its original orbit and then captured again under new gravitational influences, it may end up in a retrograde motion. The possibility of such dramatic rearrangements suggests that many planetary systems experience periods of instability before settling into their final configurations. Beyond these theories, the idea of rogue planets that have been ejected from their original solar systems and later captured by another star's gravity, raises even more questions. If a planet is drawn in from interstellar space, it is highly unlikely to align perfectly with the prograde motion of its new host star. Instead, it may enter into an orbit that is tilted, eccentric, or even fully retrograde. If retrograde planets are found to be disproportionately represented in exoplanet surveys, it could suggest that interstellar planetary migration is more common than previously thought. These scenarios lead to an even deeper question: how stable are retrograde planets in the long term? If a planet's retrograde motion is the result of a violent past, does that mean it is more prone to being ejected from its solar system in the future? Could some of these planets be on unstable trajectories that will eventually lead to their destruction? Understanding the longevity of retrograde orbits is critical not just for planetary science but also for the broader study of how solar systems evolve over billions of years. Another key factor to consider is the impact of retrograde motion on a planet's climate and atmospheric dynamics. The rotational direction of a planet plays a major role in shaping weather patterns, ocean currents, and atmospheric circulation. If a planet orbits in the opposite direction of its star's rotation, it may experience extreme weather conditions, including violent storms, chaotic wind patterns, and unpredictable seasonal changes. These factors could make life on a retrograde planet much more difficult, but not necessarily impossible. The case of Venus in our own solar system provides an interesting comparison. While Venus is not a retrograde planet in terms of its orbit, it does rotate in the opposite direction of most planets in the solar system. This unusual rotation contributes to its extreme climate, with thick clouds trapping heat and creating a runaway greenhouse effect. If a retrograde exoplanet has a similarly slow or reverse rotation, its climate could be even more extreme, with long days and nights, extreme temperature variations, and atmospheric phenomena unlike anything seen on Earth. Despite these challenges, retrograde planets could still have stable environments in certain conditions. If a planet has a strong magnetic field, for example, it could protect its atmosphere from being stripped away by stellar winds. If it has a thick atmosphere, it could regulate temperature more effectively, preventing extreme fluctuations. These factors suggest that while retrograde motion might pose challenges, it does not necessarily rule out the possibility of life. In addition to the physical and climatic challenges, retrograde planets also raise interesting questions about planetary system formation on a cosmic scale. If many planetary systems contain retrograde worlds, it suggests that the processes leading to such orbits are more common than once believed. This could mean that planetary systems are much more chaotic and dynamic than previously assumed, with planets frequently changing orbits, colliding, or being ejected into interstellar space. The implications of these findings extend beyond planetary science and into the broader study of the galaxy's evolution. If retrograde planets are common, it suggests that gravitational disruptions, including those caused by passing stars, galactic tides, and even dark matter interactions, play a significant role in shaping planetary systems. This means that the architecture of solar systems is not set in stone from the moment of formation but instead continues to evolve over billions of years. Looking ahead, the next generation of space telescopes will provide even more detailed insights into retrograde planets. Instruments like the James Webb Space Telescope, the upcoming Extremely Large Telescope, and other advanced observatories will allow astronomers to analyze the atmospheres of these strange worlds, searching for chemical signatures that could indicate their origins. If we can determine the compositions of retrograde planets and compare them to prograde ones, we may be able to identify patterns that reveal how these planets formed and whether they share common characteristics. Even more exciting is the possibility of detecting biosignatures, chemical markers that suggest the presence of life, on a retrograde exoplanet. If life exists on one of these worlds, it would be a groundbreaking discovery, proving that even planets with extreme orbits and unconventional histories can still support biological activity. Such a finding would challenge many of our assumptions about what makes a planet habitable, and would expand our understanding of life's resilience in the universe. As our technology advances and our knowledge of exoplanets deepens, retrograde planets will continue to be a major area of interest for astronomers and astrophysicists. Each new discovery adds to the complexity of our cosmic understanding, showing that the universe is far more diverse and unpredictable than we ever imagined. Ultimately, the study of retrograde planets is not just about understanding how planets move, it is about unraveling the intricate dance of celestial bodies that has been playing out for billions of years. It is about recognizing that the universe is a place of constant change, where the forces of gravity, motion, and time interact in ways that often defy our expectations. And it is about the endless pursuit of knowledge, the desire to explore the unknown, and the realization that no matter how much we discover, there will always be more mysteries waiting to be solved. The enigma of retrograde planets serves as a reminder that our understanding of planetary systems is still in its infancy. The discovery of these worlds challenges the long-standing assumption that planets should naturally orbit in the same direction as their host stars' rotation. But rather than being anomalies, retrograde planets may actually be key to unlocking a more complete picture of planetary evolution, one where chaos, instability, and even destruction play just as important a role as order and predictability. One of the most exciting aspects of studying retrograde exoplanets is their potential to reveal new insights into planetary migration. The early years of a planetary system are anything but stable. As planets form within the protoplanetary disk, they interact gravitationally, shifting positions, sometimes colliding, and occasionally even being ejected into deep space. These migrations are typically assumed to follow predictable patterns, with planets either settling into stable orbits or being flung out of the system entirely. But retrograde planets show that there is a middle ground, where a planet undergoes a dramatic shift but remains gravitationally bound to its star. This raises fascinating questions about how often planetary migrations result in complete reversals of orbital motion. If retrograde planets are relatively common, it suggests that these migrations are more widespread and extreme than previously believed. It also forces us to reconsider how many planetary systems might contain hidden worlds that have undergone similar chaotic transformations but have yet to be detected. Advanced simulations have attempted to model how such migrations occur. Many suggest that interactions between gas giants are a leading cause of extreme orbital changes. When two massive planets interact, the gravitational forces at play can create dramatic shifts. One planet may be pushed into an elongated, eccentric orbit, while the other could be ejected entirely or even flung into a retrograde motion. These simulations also show that such events are not isolated incidents but rather a fundamental part of planetary system evolution. Further complicating the picture is the role of binary star systems. Many stars exist in binary or even multi-star configurations, meaning that planets in these systems are subject to additional gravitational influences. If a planet orbits one star in a binary system, the gravitational pull of the second star can exert long-term effects, potentially flipping the orbit over time. This is yet another way in which retrograde planets may form, not through sudden chaos, but through the slow and steady pull of a companion star over millions or even billions of years. But while the mechanisms behind retrograde orbits are becoming clearer, the implications of these strange planets remain a topic of ongoing debate. One of the most intriguing questions is whether such planets could ever develop life. On one hand, their unusual orbits might create harsh and unstable conditions that make life difficult, especially if the planet experiences extreme temperature fluctuations or unpredictable seasons. But on the other hand, life on Earth has demonstrated an incredible ability to adapt to extreme environments, from deep-sea hydrothermal vents to the frozen landscapes of Antarctica. If a retrograde planet has a strong enough atmosphere, it could theoretically regulate its temperature in a way that allows life to persist. Thick clouds and atmospheric circulation could distribute heat evenly, preventing extreme differences between the planet's day and night sides. If the planet has a large ocean, it could serve as a stabilizing force, absorbing and redistributing heat to maintain a more consistent climate. In this way, a retrograde planet that might seem uninhabitable at first glance could, in fact, be capable of supporting life under the right conditions. But what about intelligent life? If an advanced civilization were to evolve on a retrograde planet, how might their understanding of the universe differ from our own? Since their night sky would show an unusual motion of celestial bodies, perhaps even appearing to move backward, relative to expectations, their early astronomical theories might have taken a very different path. Their entire perspective on planetary motion, timekeeping, and even the fundamental nature of physics could be shaped by the unique conditions of their world. Even their perception of day and night cycles could be altered. If a retrograde planet has an unusual rotational period, its inhabitants might experience extremely long days or irregular seasons, potentially influencing biological rhythms. This idea adds another layer of intrigue to the study of retrograde worlds. Not only do they challenge our understanding of planetary motion, but they also force us to consider how alien civilizations might experience reality in ways completely different from our own. As our ability to detect and study exoplanets improves, retrograde planets will remain a focal point for research. The James Webb Space Telescope, along with future missions like the Nancy Grace Roman Space Telescope and upcoming ground-based observatories, will provide astronomers with unprecedented data on these strange worlds. By analyzing their atmospheres, compositions, and orbital dynamics, we may finally uncover the full story behind their existence. But beyond the scientific implications, the study of retrograde planets speaks to something deeper: the sheer unpredictability of the universe. Time and time again, nature has shown that the cosmos is far stranger and more complex than we ever imagined. Every new discovery challenges our preconceived notions, forcing us to rethink what we thought we knew. And in the case of retrograde planets, they remind us that even something as fundamental as a planet's orbit can defy expectations. As we continue our search for new worlds, each retrograde planet we find serves as a testament to the wild, dynamic processes that govern the universe. They are reminders that the cosmos is not a static place but a constantly shifting and evolving landscape. They challenge us to keep questioning, keep exploring, and keep pushing the boundaries of what we know. And perhaps, one day, they may lead us to discoveries even more profound, whether it be the revelation of new planetary formation mechanisms, the confirmation of life beyond Earth, or insights into the fundamental forces that shape the universe itself. The journey to understand retrograde planets is far from over. With every new observation, every new model, and every new discovery, we inch closer to unraveling their mysteries. And in doing so, we come to appreciate not just these strange, backward-moving worlds, but the vast and intricate dance of celestial bodies that defines our universe. The study of retrograde planets is not just about uncovering how these worlds form. It is also about understanding what they can teach us about the nature of planetary systems as a whole. Every planetary system we observe adds another piece to the cosmic puzzle, and retrograde planets represent some of the most unusual and compelling pieces of all. One of the most intriguing aspects of these planets is their relationship with their host stars. In many cases, a planet's orbit is influenced not just by its initial formation conditions but by later gravitational interactions with other planets, nearby stars, or even the residual material left over from the protoplanetary disk. These interactions can produce extreme outcomes, including the complete reversal of a planet's orbital direction. But there is another mystery lurking beneath the surface. Why do some planets remain in retrograde orbits while others do not? If retrograde motion is the result of a dramatic event, such as a close encounter with another planet or a shifting gravitational pull, then why don't all planets with similar histories eventually stabilize into prograde orbits again? This suggests that once a planet is thrown into a retrograde orbit, there may be stabilizing forces at play, perhaps a combination of gravitational influences from its star, other planets, or even tidal effects that keep it locked in place. Tidal interactions are particularly interesting when it comes to retrograde planets. Tides occur due to the gravitational pull between a planet and its star, and over long timescales, these forces can gradually alter a planet's orbit and rotation. In most cases, tidal forces tend to bring a planet's motion into alignment with its star, eventually leading to tidal locking, where one side of the planet permanently faces the star. However, for some reason, this process does not always occur with retrograde planets, or if it does, it happens much more slowly than expected. This raises the possibility that some external factor, such as an unseen planetary companion, or a past catastrophic event, is counteracting these tidal effects. There is also the question of atmospheric dynamics on these worlds. Because retrograde planets orbit in the opposite direction of their star's rotation, their atmospheric circulation patterns may be very different from what we see on Earth or even on other exoplanets. Wind patterns, cloud formations, and even weather systems could behave in unexpected ways due to the unique forces acting on these planets. Understanding these atmospheric conditions could provide valuable insights into how climate systems function under extreme conditions, and could even inform our understanding of atmospheres on rogue planets, brown dwarfs, or other unusual celestial bodies. Another significant factor to consider is the impact of retrograde motion on a planet's magnetic field. On Earth, our magnetic field is generated by the movement of molten iron within our planet's core, creating a protective shield against harmful solar radiation. But on a retrograde planet, the interactions between the planet's magnetic field and the stellar wind could be drastically different. This could influence everything from radiation levels to the potential for life to exist on the surface. If a retrograde planet orbits close to its star, it may experience extreme radiation exposure due to its unusual motion through the stellar wind. This could lead to high levels of atmospheric stripping, where the planet's atmosphere is slowly eroded away by solar particles. However, if the planet has a strong enough magnetic field, it could potentially deflect much of this radiation, allowing it to retain a stable atmosphere despite its unusual orbit. Understanding how magnetic fields operate in such extreme environments is a major area of interest for exoplanet researchers. Another critical aspect of retrograde planets is their potential to host moons. If a retrograde planet has one or more moons, how would they behave? Would they also orbit in a retrograde motion, or would they follow a more conventional path? The answer depends on how the moon was captured or formed. If the moon was originally part of the same protoplanetary disk and remained gravitationally bound to the planet throughout its chaotic migration, then it may share the same retrograde motion. However, if the moon was captured later, perhaps after the planet had already settled into its unusual orbit, then its motion could be entirely different. Some theories even suggest that large moons could play a role in stabilizing retrograde planets. Just as Earth's moon helps regulate our planet's axial tilt and climate, a massive moon could potentially exert stabilizing forces on a retrograde planet, preventing it from experiencing extreme variations in its orbit or rotation. If such a mechanism exists, it could help explain why some retrograde planets persist for billions of years without reverting to prograde motion. Another major mystery surrounding retrograde planets is their potential for habitability. While we often assume that Earth-like conditions are necessary for life, retrograde planets challenge this assumption by existing in environments that defy our traditional understanding of planetary stability. If life can survive on a world with an extreme orbit, it suggests that life in the universe may be far more adaptable than we currently imagine. For example, if a retrograde planet is located within the habitable zone of its star, the region where conditions allow for liquid water to exist, it could still support life despite its unusual motion. The key factor would be whether the planet's climate remains stable enough over long periods. If the planet experiences extreme temperature shifts due to its orbit, life would need to be highly resilient, capable of surviving in both freezing and scorching conditions. Alternatively, life could exist in subsurface oceans, similar to what scientists speculate may exist on moons like Europa and Enceladus. These possibilities force us to reconsider our definition of a habitable world. If life can thrive on a planet with an orbit that defies conventional expectations, then the search for extraterrestrial life may need to be expanded to include a much wider range of planetary environments. This could have major implications for astrobiology, as it suggests that even planets previously dismissed as uninhabitable may still hold the potential for life. As astronomers continue to discover new exoplanets, it is likely that we will find even more examples of retrograde worlds, some with properties that challenge our understanding even further. Future telescopes will allow us to analyze their atmospheres in greater detail, searching for signs of water vapor, organic molecules, and even potential biosignatures. If we do find evidence of life on one of these worlds, it would be one of the most groundbreaking discoveries in the history of science. But even if retrograde planets turn out to be barren and lifeless, they still offer a glimpse into the incredible diversity of planetary systems. They demonstrate that the universe is filled with surprises, where the forces of nature shape worlds in ways that defy expectation. And in studying them, we not only learn more about how planets evolve, we also gain a deeper appreciation for the vast, intricate, and unpredictable cosmos we inhabit. One of the most fascinating implications of retrograde planets is what they reveal about the chaotic nature of planetary system formation. While our own solar system appears relatively orderly, with all planets orbiting in the same direction as the Sun's rotation, the discovery of exoplanets with completely different orbital behaviors suggests that the universe is far more diverse than we once believed. Retrograde motion challenges the classical models of how planets form and forces astronomers to consider alternative explanations for planetary evolution. One possible explanation for the existence of retrograde planets involves violent past interactions with other celestial bodies. In a young planetary system, planets are not always in stable orbits. They can interact with one another gravitationally, leading to close encounters, ejections, and even collisions. In some cases, a planet may be flung into a highly eccentric orbit that later stabilizes in a retrograde direction. This suggests that some retrograde planets could have once been prograde worlds that underwent extreme gravitational disturbances. The presence of a binary star system, or a passing rogue star, could also explain how some planets end up in backward orbits. When a planetary system is influenced by the gravitational pull of a nearby star, it can dramatically alter the orbits of its planets. If a star passes close enough to a planetary system, it could exert enough force to disrupt planetary orbits, flipping some of them into retrograde motion. This kind of external gravitational influence is known as the correlative mechanism, and it has been proposed as one of the leading explanations for why certain exoplanets orbit in the opposite direction of their host star's rotation. One particularly extreme case of retrograde motion can be found in systems where a planet orbits its star at an unusually close distance. In these cases, the star's gravitational forces can create significant tidal interactions that alter the planet's rotation and even its atmospheric dynamics. If a retrograde planet is close enough to its star, it may experience tidal heating, where the friction generated by gravitational forces causes the planet's interior to heat up. This could lead to intense volcanic activity, surface instability, or even the complete resurfacing of the planet over time. Such conditions could make retrograde planets some of the most extreme environments in the universe. If a planet is both retrograde and tidally locked, meaning one side always faces its star, it could have one hemisphere that is perpetually scorched while the other remains frozen in eternal darkness. In this scenario, the boundary between these two extremes, known as the terminator line, could be the only region where conditions are suitable for life. Scientists have proposed that if life were to exist on such a world, it might be concentrated along this thin habitable zone, where temperatures remain moderate enough for liquid water to exist. Another major question surrounding retrograde planets is whether they could have formed in their current state, or if they were altered after their initial formation. Most current models of planet formation suggest that planets should naturally form in prograde orbits, as they develop from the rotating disk of gas and dust surrounding a young star. If this is true, then retrograde planets must have undergone significant external influences at some point in their history. However, some researchers have suggested that under certain conditions, retrograde planets might form naturally. In a highly turbulent protoplanetary disk, complex gravitational interactions between gas, dust, and newly forming planets could create regions where motion becomes chaotic. If a planet forms in a particularly turbulent region of the disk, it might be influenced by shifting forces that cause it to develop a retrograde orbit from the very beginning. While this is still a subject of debate, it opens up the possibility that not all retrograde planets are the result of later disturbances. Some may have been born that way. A key challenge in understanding retrograde planets is that they are difficult to observe directly. Because exoplanets are typically discovered using indirect methods, such as detecting the slight dimming of a star when a planet passes in front of it or measuring the gravitational wobble of a star caused by an orbiting planet, it can be challenging to determine the exact nature of a planet's orbit. However, with advancements in telescope technology, astronomers are beginning to gather more detailed data on these unusual worlds. One of the most important tools for studying exoplanets is the radial velocity method, which measures the tiny shifts in a star's spectrum caused by the gravitational pull of an orbiting planet. By analyzing these shifts over time, astronomers can determine whether a planet is orbiting in a prograde or retrograde direction. The more detailed these measurements become, the better scientists can understand how common retrograde planets are and what conditions lead to their formation. Another promising technique for studying retrograde planets involves direct imaging. While most exoplanets are too far away to be observed directly, advances in telescope technology, such as the development of the James Webb Space Telescope and future next-generation observatories, are making it increasingly possible to capture images of distant planets. If astronomers can directly observe a retrograde planet, they may be able to study its atmospheric composition, surface conditions, and even potential weather patterns in unprecedented detail. If retrograde planets turn out to be more common than expected, it could force a major revision of our understanding of planetary formation. It would suggest that planetary systems are far more dynamic and chaotic than previously believed, with planets regularly experiencing extreme shifts in their orbits over time. This would have major implications for our understanding of the early history of our own solar system and could even provide clues about the long-term future of planetary orbits. In the search for extraterrestrial life, retrograde planets represent a fascinating unknown. While they may seem like unlikely candidates for habitability, their existence challenges our assumptions about what kinds of worlds could support life. If life is found on a retrograde planet, it would demonstrate that life can thrive under a far wider range of conditions than we currently imagine. It would also suggest that life in the universe is more resilient and adaptable than we ever thought possible. But even if retrograde planets turn out to be barren and inhospitable, they still hold immense value in our quest to understand the cosmos. They serve as natural laboratories for studying the effects of extreme gravitational interactions, planetary migration, and the long-term evolution of planetary systems. Every retrograde planet discovered adds another layer to our understanding of the universe, helping to refine our theories and expand our knowledge of what is possible in the vast, ever-changing expanse of space. As we continue to explore the universe, retrograde planets will remain one of the most intriguing mysteries in astrophysics. Their existence defies expectations, challenges established theories, and pushes the boundaries of what we think we know about planetary systems. With each new discovery, we move one step closer to unraveling the full story of how these extraordinary worlds came to be, and what they can teach us about the fundamental forces that shape the cosmos. The more we study retrograde planets, the more they challenge our assumptions about planetary formation and evolution. In traditional models of planetary system development, planets are expected to form within the rotating disk of gas and dust surrounding a young star. This means that their orbits should naturally align with the star's rotation. However, the existence of retrograde planets suggests that some worlds undergo extreme changes after their formation, or that our understanding of planetary formation is incomplete. One of the leading theories for how retrograde planets come to exist involves a process known as planetary migration. In the early stages of a planetary system's development, giant planets can move significantly from their original positions due to interactions with the protoplanetary disk or other massive bodies. This migration can lead to planets being ejected, thrown into eccentric orbits, or even captured into retrograde motion through gravitational interactions. If a planet initially formed in a standard prograde orbit but later experienced a close encounter with another massive body, it could be slingshot into an orbit that moves in the opposite direction of its star's rotation. Another possible mechanism involves so-called hot Jupiters, gas giant planets that orbit extremely close to their stars. These planets are thought to form much farther from their stars before migrating inward due to interactions with the protoplanetary disk or gravitational influences from other planets. In some cases, these migrations can involve high-energy interactions that flip a planet's orbit into a retrograde configuration. Some models suggest that if a gas giant undergoes an extreme migration event, such as being pulled inward due to the correlative mechanism, it may end up in a tilted or even fully retrograde orbit. The correlative mechanism is a process where a third massive body, such as a distant star or a large planet, perturbs the orbit of a planet, causing its inclination to oscillate dramatically over time. This effect can push a planet's orbit to extreme angles, even causing it to become retrograde. If a planetary system has a distant companion star or a particularly massive planet exerting gravitational influence, it could significantly disrupt the orbits of other planets in the system. Over millions of years, this mechanism could flip a planet's orbit completely, creating a retrograde world. One of the most intriguing aspects of retrograde planets is what they can reveal about the chaotic nature of planetary systems. Unlike the relatively stable and orderly solar system we inhabit, other planetary systems appear to be far more dynamic and unpredictable. The presence of retrograde planets suggests that massive gravitational disruptions may be common in the evolution of planetary systems, leading to unexpected orbital configurations. If such disruptions were frequent in the early universe, they could have played a significant role in shaping the diversity of planetary systems we observe today. Another major area of interest is whether retrograde planets can support life. While extreme gravitational interactions and orbital shifts might seem to make retrograde planets inhospitable, some scientists believe that life could still emerge in such environments. If a retrograde planet has a stable orbit and a protective atmosphere, it could potentially maintain conditions suitable for life. Some researchers have even suggested that retrograde motion might contribute to unique climate patterns that could support habitable conditions in ways we do not yet fully understand. For example, if a retrograde planet is also tidally locked to its star, meaning that one side is perpetually facing the star while the other remains in darkness, it could develop a distinct habitable zone along the terminator line, the region where day and night meet. In such cases, the planet's unusual orbital dynamics might create stable conditions in narrow bands where temperatures remain moderate enough for liquid water to exist. This raises the possibility that retrograde planets could host life in ways that challenge our current models of planetary habitability. Another important consideration is whether retrograde planets are more likely to have moons or rings. In our own solar system, large planets like Jupiter and Saturn have extensive moon systems that form from the rotating disks of materials surrounding them. If a retrograde planet formed in a similar way, it might have a set of moons that also exhibit unusual orbital behaviors. Alternatively, if a retrograde planet captured its moons from elsewhere in the system, they might follow irregular orbits that further complicate our understanding of planetary dynamics. Observing these planets is a significant challenge. Because most exoplanet detection methods rely on indirect observations, determining whether a planet is retrograde requires detailed measurements of its star's motion and light variations. One of the primary techniques for studying exoplanets is the radial velocity method, which detects the gravitational pull a planet exerts on its star. By analyzing shifts in the star's spectral lines over time, astronomers can infer whether a planet is moving in the same direction as the star's rotation, or in the opposite direction. Another method, known as the transit method, involves detecting the small dips in a star's brightness when a planet passes in front of it. While this method does not directly reveal whether a planet is in a retrograde orbit, it can provide crucial data about the planet's size, orbit, and potential atmospheric composition. When combined with other observational techniques, the transit method helps astronomers piece together a more complete picture of a planet's motion. Future telescopes, such as the James Webb Space Telescope and upcoming space-based observatories, may provide even more detailed insights into retrograde planets. These advanced instruments will allow scientists to analyze the atmospheres of exoplanets in unprecedented detail, searching for signs of chemical compositions that might indicate habitable conditions, or even the presence of life. If a retrograde planet has an atmosphere with signs of water vapor, oxygen, or other life-supporting molecules, it would be a groundbreaking discovery that challenges our understanding of where life can exist. The implications of retrograde planets extend beyond just exoplanet research. They also offer insights into the early history of planetary systems and the fundamental processes that shape the cosmos. If retrograde planets are found to be common, it would suggest that planetary systems are far more dynamic than previously believed, with frequent gravitational interactions leading to dramatic changes in orbital configurations. This would have major implications for our understanding of how planets form, evolve, and interact with their host stars over billions of years. In the broader search for extraterrestrial life, retrograde planets represent an intriguing possibility. While they may seem like extreme and inhospitable worlds, their very existence challenges our assumptions about planetary habitability. If life can arise on a retrograde planet, it would suggest that the universe is far more adaptable than we currently imagine. It would also expand our definition of what makes a planet suitable for life, opening up new possibilities in the search for habitable worlds beyond our solar system. Ultimately, retrograde planets are a reminder of the vast complexity and diversity of the universe. They defy conventional expectations, challenge our scientific models, and force us to rethink what we know about planetary systems. With each new discovery, astronomers gain a deeper understanding of the forces that shape the cosmos, bringing us closer to answering some of the most profound questions about the nature of planets, the formation of solar systems, and the potential for life beyond Earth. As technology advances and our ability to observe distant worlds improves, the study of retrograde planets will continue to evolve. Each new discovery adds another piece to the puzzle, helping to refine our theories and expand our knowledge of the universe. Whether they are the result of violent gravitational interactions, remnants of ancient planetary migrations, or products of unique formation processes, retrograde planets remain one of the most fascinating and mysterious phenomena in astrophysics. With every step forward, we come closer to unraveling the secrets of these extraordinary worlds. The more we learn, the more we realize that the universe is full of surprises, and that the mysteries of space are far from being fully understood. The study of retrograde planets continues to reveal just how chaotic and unpredictable planetary systems can be. Unlike the relatively stable and orderly arrangement of our own solar system, many exoplanetary systems appear to be shaped by violent gravitational interactions, collisions, and complex orbital dynamics. Retrograde planets, in particular, highlight the extreme ways in which planetary orbits can evolve, defying our expectations and forcing us to reconsider the processes that govern planetary formation and migration. One of the biggest mysteries surrounding retrograde planets is the question of their atmospheres. If a planet forms in a typical prograde orbit and later becomes retrograde due to gravitational interactions, what happens to its atmosphere? Does it remain intact, or do these extreme changes strip it away? The answer to this question could provide crucial insights into planetary habitability and the potential for life beyond Earth. In some cases, a planet undergoing a retrograde transformation might experience significant atmospheric loss. If a planet is thrown into a highly eccentric orbit or subjected to strong tidal forces from its star, its atmosphere could be eroded over time. This is particularly true for planets that migrate too close to their stars, where intense stellar radiation can strip away lighter gases, leaving behind only a dense core. However, some retrograde planets might retain their atmospheres, particularly if they have strong magnetic fields or if they migrate to a stable orbit after their initial disruption. Another intriguing question is whether retrograde planets could have unique climate patterns due to their unusual motion. If a planet orbits its star in the opposite direction of the star's rotation, it could experience unusual day-night cycles, extreme weather patterns, and temperature variations that differ from those on prograde planets. Some scientists speculate that these effects could create stable zones where liquid water, and potentially life, could exist in ways we do not yet fully understand. For example, if a retrograde planet is tidally locked, meaning that one side always faces its star while the other remains in perpetual darkness, it could develop a stable climate along the terminator line, the region where day and night meet. This narrow strip of moderate temperatures could provide a refuge for liquid water, making it one of the most likely places for life to emerge. While we do not yet have direct evidence of life on retrograde planets, these unique conditions suggest that they should not be dismissed as entirely inhospitable. The discovery of retrograde planets has also led scientists to rethink the classification of planetary systems. Traditionally, we have categorized exoplanets based on their size, composition, and distance from their host stars. However, retrograde planets challenge these classifications, as they suggest that planetary systems are far more dynamic than previously believed. If planetary migration, gravitational interactions, and orbital flips are common, then many planets may not fit neatly into existing categories. Instead, we may need new frameworks to describe planetary systems that account for their chaotic evolution. As technology advances, our ability to study retrograde planets in greater detail is improving. Upcoming space telescopes, such as the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, ELT, will provide even more precise measurements of exoplanetary atmospheres, orbits, and compositions. These instruments will allow scientists to detect subtle changes in starlight caused by planetary transits, revealing whether a planet's orbit is prograde or retrograde with greater accuracy than ever before. One of the most exciting possibilities is that future telescopes might detect biosignatures, chemical markers that suggest the presence of life, on retrograde planets. If we find an exoplanet with an atmosphere rich in oxygen, methane, or other light-related gases, it would be a groundbreaking discovery that challenges our assumptions about planetary habitability. Such a finding would suggest that life can emerge and survive even on planets with extreme and unexpected orbital characteristics. Beyond their implications for exoplanetary science, retrograde planets also raise fundamental questions about the nature of planetary systems across the universe. If retrograde orbits are relatively common, then it suggests that planetary systems are far more diverse than previously thought. It also implies that the processes governing planetary formation and evolution are more complex than our current models predict. Some researchers have even speculated that retrograde planets could play a role in the long-term stability of planetary systems. If a massive retrograde planet exists in a system, it might act as a gravitational stabilizer, preventing other planets from migrating too close to the star or colliding with each other. Alternatively, retrograde planets might indicate that a system has undergone major disruptions in the past, hinting at violent cosmic events such as planetary ejections or stellar flybys. Another possibility is that retrograde planets could be relics of ancient planetary collisions. If a planet formed in a prograde orbit but later experienced a massive impact with another large body, the collision could alter its motion and push it into a retrograde trajectory. This idea aligns with some theories about the formation of Earth's moon, which suggests that a giant impact early in Earth's history played a crucial role in shaping its orbit and rotation. If similar events occurred in other planetary systems, they could explain the existence of retrograde planets. Despite the progress we have made in understanding retrograde planets, many questions remain unanswered. How common are these planets? Do they form in specific types of systems, or can they appear anywhere? Are retrograde orbits more stable than prograde ones in certain conditions? As we continue to explore the universe, the answers to these questions will shape our understanding of planetary systems and their potential to host life. Ultimately, the study of retrograde planets is a testament to the ever-evolving nature of astronomy. Each new discovery challenges our assumptions, forces us to refine our models, and opens up new possibilities for exploration. As we peer deeper into the cosmos, we will undoubtedly uncover even more mysteries, some of which may redefine our understanding of the universe itself. The existence of planets that orbit backward serves as a powerful reminder that the universe is far more complex and unpredictable than we once imagined. From the intricate dance of gravitational forces to the chaotic history of planetary migrations, these worlds tell a story of cosmic evolution filled with surprises. As we continue to search for new exoplanets and analyze their properties, we may one day discover a retrograde world that harbors life, challenging our understanding of what makes a planet habitable and reshaping our place in the cosmos. If a retrograde planet capable of supporting life were to be discovered, it would challenge many of our assumptions about habitability. Scientists currently focus their search for life on planets that share similarities with Earth, rocky worlds in the habitable zone of their stars, with stable orbits and predictable climates. But what if life has adapted to thrive in conditions we would typically consider extreme? Retrograde planets, with their unusual orbital patterns and potential for chaotic climates, might host forms of life that evolved under entirely different conditions than those on Earth. One possibility is that life on a retrograde planet could be more resilient to environmental changes. If a planet's orbit has undergone a major shift in the past, perhaps due to a gravitational interaction or a violent collision, any life that survived would have needed to adapt to dramatic shifts in temperature, atmosphere, and radiation exposure. Such an environment could lead to organisms with extreme adaptability, capable of withstanding conditions that would be fatal to life on Earth. Another fascinating question is whether the reversed orbital motion of a planet could affect its magnetic field. Earth's magnetic field is generated by the movement of molten iron in its core, driven in part by the planet's rotation. If a retrograde planet had its rotation altered by an extreme event, could that also disrupt its magnetic field? A weaker or irregular magnetic field could have profound consequences for life, as it would expose the planet's surface to higher levels of cosmic radiation. On the other hand, if the planet managed to maintain a strong magnetic field despite its retrograde motion, it might still offer protection for potential life forms. The effects of a retrograde orbit could extend beyond a single planet. It could impact the entire system. If one planet in a system is retrograde, it suggests that the system has experienced significant gravitational disturbances in the past. Could these disturbances also affect the stability of other planets in the system? If so, a retrograde planet could be a sign that its planetary neighbors are also in unusual orbits, potentially creating a system filled with worlds that challenge our expectations. Another area of study involves the atmospheres of retrograde planets. A planet's atmosphere is influenced by many factors, including its distance from its star, its rotation, and its magnetic field. On a planet with an extreme orbit, atmospheric circulation patterns might be vastly different from those on Earth. Winds, cloud formation, and temperature distribution could behave in unexpected ways, possibly leading to unique climate patterns that could either hinder or support life. One intriguing possibility is that some retrograde planets could have exceptionally long days and nights. If a planet's retrograde motion is combined with a slow rotation, it could result in days that last for months or even years. Such a planet might experience extreme temperature variations, with one side baking under constant sunlight, while the other remains in freezing darkness. However, if an atmosphere is thick enough, it might help regulate temperatures, distributing heat more evenly across the planet's surface. The presence of retrograde planets also raises questions about the broader dynamics of planetary migration. If many exoplanets experience significant changes in their orbits over time, it suggests that planetary systems are not as stable as they might appear. Some scientists have proposed that our own solar system may have had planets that were ejected in the distant past due to gravitational interactions. If retrograde motion is a sign of such interactions, then studying these planets could help us understand the history of planetary systems, including our own. Another theory suggests that some retrograde planets might be captured exoplanets, worlds that formed around one star but were later pulled into orbit around another. This could happen in densely packed star systems where gravitational forces are strong enough to disrupt planetary orbits. If this is the case, then some retrograde planets could have originated in entirely different environments before settling into their current positions. This raises exciting possibilities. Could life survive such an extreme journey? If a planet was ejected from one system and later captured by another, could any microbial life forms present on that world endure the transition? Such a scenario would have profound implications for the possibility of interstellar panspermia, the idea that life can spread between star systems by hitching a ride on planets or asteroids. If a retrograde planet was once part of a different planetary system, it might carry traces of an entirely different biosphere. Detecting such evidence would be one of the most groundbreaking discoveries in the history of science, suggesting that life might not be confined to a single origin but could instead be a shared feature of multiple star systems. Even without life, the study of retrograde planets has profound implications for understanding planetary formation and evolution. The fact that these planets exist at all suggests that planetary systems are far more chaotic than we once believed. Instead of forming in neatly ordered orbits that remain stable over billions of years, many planets might experience dramatic changes, shifting from prograde to retrograde motion, being flung into eccentric orbits, or even being ejected entirely from their systems. Future space missions will provide even greater insights into these mysterious worlds. Upcoming telescopes like the James Webb Space Telescope and the European Space Agency's Ariel mission are designed to analyze the atmospheres of exoplanets in unprecedented detail. These instruments could detect chemical signatures in the atmospheres of retrograde planets, revealing whether they have conditions suitable for life. In addition, advancements in computer modeling are helping scientists simulate how retrograde planets form and evolve. By recreating the conditions that lead to these unusual orbits, researchers can test different theories about planetary migration, gravitational interactions, and planetary collisions. These simulations provide valuable clues about the history of planetary systems and help refine our models of how planets interact over billions of years. As we continue to discover more exoplanets, it is likely that we will find even more retrograde worlds, some of which may be unlike anything we have seen before. Perhaps there are planets with highly elliptical retrograde orbits, planets that switch between prograde and retrograde motion over time, or even planets that orbit in complex resonance patterns with their neighbors. Each new discovery will add to our understanding of the vast diversity of planetary systems and challenge us to rethink our assumptions about how planets behave. The existence of retrograde planets serves as a reminder that the universe is full of surprises. Every time we think we have a clear understanding of how planets form and evolve, new discoveries force us to reconsider our theories. Retrograde planets are just one example of how reality can defy our expectations, revealing a cosmos that is more complex, dynamic, and unpredictable than we ever imagined. The search for life beyond Earth is one of the greatest scientific quests of our time, and retrograde planets represent an intriguing piece of the puzzle. Whether they turn out to be barren, chaotic worlds or hidden havens for life, their existence reshapes our understanding of planetary science and opens new possibilities for exploration. As we develop better technology and refine our methods of detection, the mysteries of these worlds will become clearer, bringing us one step closer to answering some of the biggest questions about the universe. The discovery of a truly Earth-like retrograde planet, complete with a stable atmosphere, liquid water, and a habitable climate, would be a revelation. It would show us that life can exist in places we never thought possible, and that the universe is even more diverse than we ever imagined. Until then, the study of retrograde planets continues to push the boundaries of what we know, driving us toward new discoveries and deeper insights into the vast and mysterious cosmos. The implications of retrograde planets extend beyond planetary science and into the fundamental nature of astrophysics itself. The existence of these worlds suggests that our understanding of planetary formation is still incomplete, raising profound questions about the stability and evolution of entire solar systems. Could retrograde planets be a natural stage in the life cycle of planetary systems, or are they rare anomalies created by extraordinary events? One possible clue lies in the fact that some retrograde planets exist in multi-planet systems. This suggests that their backward motion does not necessarily destabilize the entire system, meaning that such orbits can be sustained over long periods. However, the presence of a retrograde planet could indicate past instabilities. Perhaps other planets were ejected, or the system underwent a phase of intense gravitational reshuffling. If retrograde motion is a marker of past chaos, then these planets could serve as a historical record of their system's violent past. Observing retrograde exoplanets also provides insight into how planetary atmospheres evolve under unusual conditions. Planets with highly tilted orbits may experience extreme seasonal variations, affecting atmospheric circulation in ways not seen on Earth. For example, on a retrograde planet with a high axial tilt, the poles might receive more sunlight than the equator at certain times of the year, reversing typical weather patterns. The study of such worlds could help refine climate models and improve our understanding of planetary habitability. The concept of retrograde motion also raises intriguing questions about the potential for life to develop intelligence. On Earth, the stability of day-night cycles, seasonal variations, and long-term climate patterns have all played a role in the evolution of life. If a planet experiences extreme shifts in temperature or unpredictable climate events due to its retrograde orbit, could intelligent life evolve in such an environment? Would such beings develop unique survival strategies, perhaps evolving faster due to the constant environmental pressures? Furthermore, retrograde planets challenge our assumptions about planetary system formation. The standard model of planet formation suggests that planets form from a rotating disk of gas and dust, leading to a general alignment of planetary orbits. The existence of retrograde planets indicates that gravitational interactions, stellar flybys, and even interstellar migrations could play a larger role in shaping planetary systems than previously thought. If entire planets can be thrown into reversed orbits, what else might be possible? Another fascinating aspect of retrograde planets is their potential to host moons. If a retrograde planet has one or more moons, their own orbital dynamics would be highly complex. Depending on how they were captured or formed, these moons might also orbit in retrograde motion relative to their planet, or they could maintain a standard orbit while their host world moves in the opposite direction. Understanding such systems could provide further insight into how gravity sculpts the architecture of planetary environments. One of the most exciting developments in exoplanet research is the possibility of directly imaging these strange worlds. While most exoplanets are detected through indirect methods like transit photometry or radial velocity measurements, advances in telescope technology may soon allow us to capture actual images of planets orbiting other stars. A direct image of a retrograde planet could reveal surface features, cloud patterns, and even signs of atmospheric composition, giving us an unprecedented look at how these unique worlds function. Future telescopes, such as the Extremely Large Telescope, ELT, and the Habitable Worlds Observatory, will have the resolution and sensitivity needed to study retrograde planets in greater detail. By analyzing the light reflected from their atmospheres, astronomers can determine what gases are present and whether they have conditions suitable for life. This research could ultimately redefine our search for habitable worlds, expanding our understanding of where life might arise in the universe. Another key area of study involves the potential link between retrograde planets and rogue planets, worlds that have been ejected from their home systems and now drift through interstellar space. If gravitational disruptions are powerful enough to flip a planet's orbit, they might also be capable of ejecting planets entirely. Could some retrograde planets be former rogue planets that were later captured by a new star? If so, they might carry unique chemical signatures that reveal their interstellar origins. This brings us to one of the most speculative but fascinating possibilities: the idea that retrograde planets could be homes to ancient alien civilizations. If a civilization developed on a retrograde world, it might have a completely different perspective on the universe. Their understanding of celestial mechanics, timekeeping, and even fundamental physics could differ from ours due to their unique planetary environment. The existence of retrograde planets adds yet another layer to the complexity of astrobiology, showing that life, if it exists beyond Earth, might emerge under conditions far stranger than we have ever imagined. Additionally, the study of retrograde planets has important implications for planetary defense. If our own solar system experienced gravitational chaos in the past, leading to the ejection or alteration of planetary orbits, could such events happen again? Understanding how planets transition into retrograde motion could help us predict future disruptions that might affect Earth or other planets in our solar system. The long-term stability of planetary orbits is crucial for understanding the future evolution of the cosmos. If retrograde planets are more common than previously thought, it might indicate that planetary systems undergo continual reshuffling over billions of years. This could challenge the idea that solar systems remain stable for long periods, suggesting instead that planets might frequently change their positions, orbits, and even their host stars. As research continues, scientists are uncovering more examples of planetary systems with unexpected characteristics. The discovery of hot Jupiters, gas giants that orbit extremely close to their stars, was once considered a major anomaly, but they are now understood as a natural result of planetary migration. Similarly, retrograde planets may soon be recognized as a common consequence of the dynamic and often violent processes that shape planetary systems. The discovery of retrograde planets has already rewritten some of our assumptions about how the universe works, but many questions remain. What percentage of planetary systems contain retrograde planets? Are there entire systems where most or all planets orbit backward? Could there be planets that switch between prograde and retrograde motion over time? Ultimately, the study of retrograde planets is a testament to the boundless curiosity of human exploration. Every time we uncover something unexpected, it forces us to refine our theories and seek new explanations. These strange, backward-orbiting worlds challenge our understanding of planetary formation, gravitational dynamics, and even the potential for life beyond Earth. They remind us that the universe is not just stranger than we imagine, it is stranger than we can imagine. As our technology improves and our ability to study distant worlds expands, we will continue to uncover new mysteries hidden in the vast expanse of space. Retrograde planets may be just the beginning of a deeper realization that the cosmos is far more dynamic, chaotic, and unpredictable than we ever believed. And with each new discovery, we come one step closer to understanding the true nature of our universe. The study of retrograde planets represents just one piece of the larger puzzle of planetary science. As we continue to explore these enigmatic worlds, we must also consider how they fit into the broader framework of exoplanetary research. The search for planets beyond our solar system has revealed an astonishing diversity of worlds, from scorching lava planets to ice giants shrouded in dense atmospheres. Each new discovery challenges our understanding of planetary formation and dynamics, forcing us to rethink what is possible in the cosmos. One of the most intriguing aspects of retrograde planets is their potential to host unusual geological and atmospheric processes. On Earth, our planet's rotation and orbit influence everything from weather patterns to ocean currents. If a planet orbits in the opposite direction of its star's rotation, the interplay between atmospheric winds and the planet's motion could create bizarre and extreme weather phenomena. For instance, a planet with a thick atmosphere might experience winds that spiral in unexpected directions, creating chaotic storm systems unlike anything seen on Earth. Another mystery surrounding retrograde planets is how they might influence the evolution of their host stars. In most planetary systems, planets are thought to exert a stabilizing effect on their stars, helping to regulate their rotation over time. However, if a planet orbits in the opposite direction, it could exert unusual gravitational forces that disrupt the star's rotation, potentially altering its magnetic activity or even influencing its lifespan. Understanding these interactions could provide valuable insights into the long-term evolution of planetary systems. The presence of retrograde planets also has implications for the search for extraterrestrial life. Most of our efforts to identify habitable exoplanets have focused on worlds that resemble Earth, planets with stable climates, predictable day-night cycles, and conditions conducive to liquid water. But if life can adapt to extreme environments on Earth, such as deep-sea hydrothermal vents or acidic lakes, could it also survive on a retrograde planet with erratic seasons and unusual climate patterns? The discovery of life on such a world would revolutionize our understanding of biology and expand the possibilities for where life might exist in the universe. One possibility is that retrograde planets could host subsurface oceans, similar to what we see on icy moons in our solar system. If a retrograde planet is located in the habitable zone of its star but experiences extreme surface conditions, life might still thrive beneath the surface, protected from harsh radiation and temperature fluctuations. This would mean that even seemingly inhospitable worlds could still be candidates for life, challenging the traditional notion of habitability. There is also the question of how common retrograde planets truly are. The current methods used to detect exoplanets, such as the transit method and radial velocity measurements, are more effective at identifying large planets in close orbits. This means that many retrograde planets, particularly smaller ones or those orbiting farther from their stars, could still be undiscovered. As telescope technology improves, we may find that retrograde motion is far more common than we initially thought, reshaping our understanding of planetary formation. Looking forward, upcoming space missions and advanced observatories will play a crucial role in unraveling the mysteries of retrograde planets. The James Webb Space Telescope, JWST, has already begun providing detailed atmospheric analyses of exoplanets, and future telescopes like the European Extremely Large Telescope, ELT, will further enhance our ability to study distant worlds. By combining data from multiple observatories, scientists can refine their models and develop a more comprehensive picture of how retrograde planets form and evolve. The discovery of retrograde planets also has implications for planetary defense. If gravitational interactions can drastically alter the orbits of planets, what does this mean for asteroids and comets? Could similar gravitational forces push a rogue asteroid onto a collision course with Earth? Understanding how planetary orbits change over time could help scientists predict potential cosmic threats and develop strategies to mitigate them. Furthermore, retrograde planets challenge some of our most fundamental assumptions about how celestial bodies interact. If planets can orbit in the opposite direction of their star's rotation, what other unexpected phenomena might exist in the universe? Could there be entire planetary systems that defy our current models of formation? The more we learn about these unusual worlds, the more we realize how much we still have to discover. Ultimately, the study of retrograde planets is not just about understanding individual worlds. It's about expanding our knowledge of the universe as a whole. Each new discovery forces us to refine our theories, question our assumptions, and push the boundaries of what we thought was possible. The cosmos is a vast and mysterious place, filled with wonders beyond our imagination. And as we continue to explore, one thing is certain: the universe will always have more secrets waiting to be uncovered. One of the most fascinating aspects of retrograde planets is their potential to rewrite our understanding of planetary migration and system stability. Traditionally, we have viewed planetary formation as a relatively orderly process. Dust and gas coalesce into planets within a protoplanetary disk, and these planets settle into stable orbits around their stars. However, the existence of retrograde planets suggests that the evolution of planetary systems is far more dynamic and chaotic than we once believed. In many cases, retrograde motion is a sign that a planet has undergone significant gravitational interactions, either with other planets in its system or with an external force, such as a passing star. These interactions can lead to extreme changes in a planet's orbit, sometimes even causing it to be ejected entirely from its solar system. This raises intriguing questions about the fate of planets that experience such drastic disruptions. Could some retrograde planets have been on the verge of becoming rogue planets, worlds that wander through interstellar space with no star to orbit, only to be captured by a new system at the last moment? If retrograde planets were once interstellar wanderers, they might carry unique chemical signatures that set them apart from their native-born counterparts. Studying their compositions could provide clues about where they originally formed, revealing the processes that govern planet formation in different parts of the galaxy. This could be particularly valuable in understanding how planetary systems evolve over billions of years and whether similar processes occurred in our own solar system's past. Another mystery surrounding retrograde planets is whether they can sustain moons or even entire moon systems. In our solar system, moons tend to orbit their planets in the same direction as the planet's rotation, a natural consequence of the way planetary systems form. However, if a planet orbits its star in retrograde motion, the gravitational interactions that govern moon formation could become highly unpredictable. Some moons might end up orbiting in the opposite direction of their host planet's rotation, while others might be ejected entirely. A retrograde planet with a stable moon system would be an astrophysical oddity, providing further evidence of the immense gravitational forces at play in these unusual worlds. If such a planet had multiple moons, their interactions could create chaotic orbital dynamics, leading to irregular eclipses and tidal forces that could affect the planet's climate and geology. Studying these systems could help scientists understand how gravity sculpts planetary environments in ways that defy our expectations. There is also the question of whether retrograde planets could host ring systems. In our solar system, rings are most commonly associated with gas giants like Saturn, where they are formed from ice and rock debris that remains in orbit around the planet. If a retrograde planet has a ring system, the gravitational forces acting on those rings could be vastly different from what we observe around prograde planets. The particles within the rings might experience unusual orbital instabilities, potentially leading to asymmetric or shifting ring structures. Observing such rings could provide valuable information about the long-term stability of retrograde planets. If these planets can maintain ring systems over millions or even billions of years, it would suggest that their orbits, while unusual, are not necessarily unstable. This would further challenge the notion that retrograde motion is an anomaly or a sign of imminent planetary destruction. Instead, it could be a natural and persistent feature of some planetary systems. Another fascinating aspect of retrograde planets is their potential impact on their host stars. In many cases, a planet's gravitational pull affects the rotation of its star over time, a process known as tidal interaction. When a planet orbits in the same direction as its star's rotation, this interaction typically leads to a gradual synchronization between the two bodies. However, when a planet moves in the opposite direction, it can create a braking effect that slows the star's rotation more dramatically. This means that the presence of a retrograde planet could influence the long-term evolution of its star, affecting everything from its magnetic field to its ability to support life on other planets in the system. If a massive retrograde planet exerts enough torque on its star, it could alter the star's activity cycles, potentially making it more or less hospitable for habitable planets in the system. Understanding these interactions could help astronomers refine their models of stellar evolution and improve predictions about the habitability of exoplanetary systems. Perhaps one of the most exciting possibilities is that retrograde planets could serve as natural laboratories for studying gravitational interactions at an extreme level. By observing how these planets interact with their stars, moons, and surrounding debris, scientists can gain new insights into the fundamental forces that govern the universe. These observations could also have practical applications, such as refining our understanding of how gravity operates on cosmic scales and improving models used in astrophysical simulations. As technology advances, our ability to study retrograde planets will only improve. The next generation of telescopes, including the European Space Agency's Plato mission and the upcoming Habitable Worlds Observatory, will provide unprecedented insights into the atmospheres and compositions of distant exoplanets. With more powerful instruments, astronomers may be able to directly image retrograde planets, revealing their surface features, cloud patterns, and even potential weather systems. The future of exoplanet research is full of exciting possibilities, and retrograde planets are just one example of how the universe continues to surprise us. Their existence challenges our assumptions, expands our understanding of planetary formation, and forces us to consider new possibilities about the nature of celestial mechanics. Each new discovery adds another piece to the puzzle, bringing us closer to answering some of the most fundamental questions about the universe and our place within it. As we continue to push the boundaries of our knowledge, one thing is certain: the study of retrograde planets is far from over. These mysterious worlds have already reshaped our understanding of planetary science, and they will undoubtedly continue to reveal new and unexpected secrets as our exploration of the cosmos advances. The search for answers will take us to the farthest reaches of space, unlocking the mysteries of worlds that defy gravity itself. The study of retrograde planets is more than just an exploration of anomalies. It is a window into the very fabric of how planetary systems evolve, interact, and sometimes defy expectations. These strange worlds challenge our conventional models, revealing that the forces shaping the cosmos are far more complex than we once thought. But beyond their scientific intrigue, retrograde planets also push us to consider deeper philosophical and existential questions. What happens when nature does not follow its own rules? How many other planetary systems operate under conditions we once deemed impossible? And what might this mean for our own place in the universe? One of the most compelling aspects of retrograde planets is their potential to exist in a variety of cosmic environments. While many of the known retrograde planets are so-called hot Jupiters, massive gas giants that orbit extremely close to their host stars, there is no fundamental reason why smaller, rocky planets could not also exhibit retrograde motion. If such planets exist, they could potentially be habitable under the right conditions. This would significantly broaden our understanding of the kinds of environments in which life might arise. A retrograde Earth-like planet, for example, would experience radically different day-night cycles and seasonal variations compared to a planet with a traditional prograde orbit. The interplay of its rotation, atmospheric currents, and stellar radiation could lead to unusual climate patterns, where temperature fluctuations are far more extreme or entirely unpredictable. Could life adapt to such conditions? If so, it would challenge many of our assumptions about habitability and what is necessary for life to thrive. There is also the possibility that some retrograde planets may have started as prograde planets before being flipped into their current state. Such a transition could result from violent collisions, gravitational interactions with nearby stars, or even the influence of a massive, unseen companion planet. If this process occurs frequently in the universe, it could mean that many planetary systems undergo radical transformations over time, reshaping our understanding of their long-term stability. This brings us to one of the most significant unanswered questions: how do retrograde planets evolve over billions of years? Do they remain in stable orbits, or are they doomed to eventual destruction? Some theories suggest that retrograde planets might be more prone to destabilization, either being thrown out of their solar systems entirely or spiraling toward their host stars. However, others propose that these planets could remain in their unusual orbits indefinitely, depending on the specific gravitational conditions of their systems. One key factor that could determine a retrograde planet's fate is the presence of other massive planets in the same system. If a retrograde planet is part of a multi-planet system, its interactions with other planets could either stabilize its orbit or lead to further chaos. In some cases, these gravitational battles might even cause planets to switch orbits, change inclinations, or be ejected into interstellar space. Such events could be responsible for the existence of rogue planets, worlds that drift through the galaxy without a star to call home. If retrograde planets can exist for billions of years, they may offer valuable clues about the history of their solar systems. By studying their chemical compositions and orbital dynamics, scientists can potentially reconstruct the events that led to their formation. This could provide a deeper understanding of how planetary systems change over time, and whether similar processes might have shaped our own solar system in the distant past. Another major mystery surrounding retrograde planets is their potential for hosting atmospheres and liquid water. In our solar system, planets and moons with thick atmospheres, such as Venus and Titan, experience strong atmospheric circulation patterns that are driven by their rotation and proximity to the Sun. On a retrograde planet, these circulation patterns could behave very differently, possibly leading to unexpected weather phenomena. For instance, if a retrograde planet has a thick atmosphere and a strong greenhouse effect, it might experience extreme heat distribution, where one hemisphere remains significantly warmer than the other. Alternatively, its atmosphere might develop unique wind patterns that stabilize its climate in ways we have yet to predict. Understanding these dynamics could help refine our models of planetary atmospheres and even improve our ability to predict climate behavior on Earth. The possibility of moons around retrograde planets also raises intriguing questions. If a retrograde planet were to have a moon that orbits in the opposite direction of the planet's own motion, the gravitational interactions between the two bodies could lead to extreme tidal forces. These forces might generate heat within the moon's interior, potentially creating subsurface oceans similar to those found on Europa and Enceladus. If life exists in such environments, it could mean that retrograde planets are not just scientific curiosities. They could be key players in the search for extraterrestrial life. The presence of retrograde planets also has implications for planetary formation theories beyond our own galaxy. As we continue to discover exoplanets in distant star systems, we may find that retrograde motion is not an isolated phenomenon but a fundamental feature of planetary evolution. If this is the case, it could mean that our understanding of how solar systems develop needs to be completely rewritten. The ongoing search for retrograde planets will likely be aided by next-generation observatories that can directly image exoplanets and analyze their atmospheres in unprecedented detail. Missions like the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, ELT, will provide astronomers with the tools needed to detect subtle variations in planetary orbits, atmospheric compositions, and even potential biosignatures. These advancements will allow us to test our theories about retrograde planets and refine our understanding of their origins. Ultimately, the study of retrograde planets is not just about answering a single question. It is about unraveling the deeper mysteries of how the universe operates. These worlds challenge our preconceived notions, forcing us to rethink the fundamental forces that shape planetary systems. They remind us that the cosmos is full of surprises and that even the most seemingly impossible phenomena can and do exist. As our technology improves and our understanding deepens, the discovery of retrograde planets may be just the beginning. The universe is vast, and its secrets are far from fully uncovered. The question is not just how many retrograde planets exist, but what other unexpected wonders are waiting to be found. The study of these strange worlds is a testament to humanity's insatiable curiosity and our relentless pursuit of knowledge. With each new discovery, we take another step closer to unlocking the deepest mysteries of the cosmos. The implications of retrograde planets stretch beyond their immediate scientific intrigue. They challenge our assumptions about the very nature of planetary systems. If these planets are more common than we once believed, what does that say about the processes that govern the universe? Could it be that planetary formation is not as orderly as we once thought, but rather a chaotic and unpredictable process, shaped by unseen forces and cosmic accidents? One of the biggest challenges in studying retrograde planets is detecting them in the first place. Most of our knowledge of exoplanets comes from the transit method, which observes the tiny dips in a star's brightness when a planet passes in front of it. However, this method alone does not reveal the direction of a planet's orbit. To determine whether a planet is moving in a retrograde direction, astronomers rely on a technique called the Rossiter-McLaughlin effect. This effect occurs when a planet transits its star and blocks part of the star's rotating surface. Because stars rotate, one side of the star moves toward us while the other moves away. When a planet passes over the side that is moving toward us, it blocks some of the blue-shifted light. When it passes over the receding side, it blocks some of the red-shifted light. By measuring these changes in the star's spectrum, astronomers can determine whether a planet's orbit aligns with the star's rotation or moves against it. What they have found is astonishing. Some planets orbit at extreme angles, while others move in nearly perfect retrograde motion. These findings suggest that planetary systems can be much more dynamic than we originally assumed. Instead of forming in neat, orderly disks, many planets may be thrown into chaotic orbits by gravitational interactions, collisions, or encounters with passing stars. One of the most puzzling discoveries is that some retrograde planets do not seem to have undergone violent disruptions. Instead, their orbits appear to have been altered by a more gradual process. This raises an important question: can retrograde motion arise naturally, without the need for a catastrophic event? Some researchers believe that certain gravitational interactions, particularly those involving distant companion stars, could slowly nudge a planet into a retrograde orbit over millions or even billions of years. For example, a process known as the correlative mechanism occurs when a planet's orbit is influenced by a distant stellar companion. If a planet orbits a star that is part of a binary system, the gravitational pull of the second star can cause the planet's orbit to oscillate dramatically over time. These oscillations can gradually tilt the planet's orbit until it becomes retrograde. This mechanism has been proposed as a possible explanation for some of the hot Jupiters that orbit their stars backward. Another possibility is that retrograde planets form in multi-star systems where gravitational forces are constantly shifting. If a planet forms around one star but is later captured by another, its orbit may end up in an unusual configuration. In some cases, this could result in a retrograde orbit, as the planet settles into a new gravitational balance. These scenarios suggest that retrograde planets might be more common than we previously thought, especially in systems with multiple stars. Given that the majority of stars in the universe are part of binary or multi-star systems, the existence of retrograde planets could be a widespread phenomenon. This also has implications for the search for habitable planets. If retrograde planets can exist in stable orbits for billions of years, it raises the possibility that some of them could support life. In fact, a retrograde planet with the right conditions might experience unique climate patterns that could make it even more hospitable than a typical prograde planet. For example, a retrograde planet with a thick atmosphere might develop unusual weather systems that help regulate its temperature. If the planet is tidally locked, meaning that one side always faces its star, it could have a permanent day side and a permanent night side. In such a scenario, the planet's retrograde motion could create strong atmospheric currents that distribute heat more efficiently, reducing temperature extremes and making the planet more habitable. The potential for life on retrograde planets is an area of growing interest. If life can adapt to extreme conditions on Earth, it is possible that alien life forms could thrive on worlds with unusual orbital dynamics. The presence of water, a stable climate, and a protective atmosphere are more critical factors for habitability than the direction of a planet's orbit. One of the most intriguing ideas is that retrograde motion could play a role in the evolution of life itself. If a planet experiences significant changes in its orbit over time, it could go through cycles of climate shifts that drive evolutionary adaptation. On Earth, mass extinctions and rapid changes in climate have played a crucial role in shaping the development of life. Could similar processes be at work on retrograde planets, pushing life to evolve in unexpected ways? As we continue to explore the universe, retrograde planets offer a fascinating glimpse into the complexity of planetary evolution. They remind us that the universe is full of surprises and that even the most unexpected phenomena can be explained through careful observation and scientific inquiry. The discovery of more retrograde planets will undoubtedly lead to new questions and challenges. Are these planets stable over long periods, Or are they destined for chaotic fates? Do they have unique geological or atmospheric features that distinguish them from prograde planets? Could some of them harbor life? As technology advances, future telescopes will provide even more detailed data on exoplanetary systems. Missions such as the James Webb Space Telescope, the upcoming Habitable Worlds Observatory, and ground-based observatories like the 30-meter telescope will allow astronomers to analyze exoplanet atmospheres with unprecedented precision. These observations will help determine whether retrograde planets are rare exceptions or common occurrences throughout the galaxy. Ultimately, the study of retrograde planets is not just about understanding individual worlds. It is about uncovering the deeper principles that govern planetary formation and evolution. Every new discovery brings us closer to answering some of the most profound questions about our universe. How do planets form? How do they change over time? And what strange and unexpected worlds might still be out there, waiting to be found? The search for exoplanets has already revolutionized our understanding of the cosmos, revealing that our solar system is just one of countless possibilities. But the discovery of retrograde planets suggests that the universe is even stranger than we imagined. If some worlds can orbit backward, what other bizarre phenomena might be out there, beyond the limits of our current knowledge? As we continue to explore, one thing is certain: the universe will never cease to amaze us. The existence of retrograde planets is just one example of how the cosmos constantly defies expectations, challenging us to expand our understanding of what is possible. With each new discovery, we step further into the unknown, uncovering secrets that will reshape our view of the universe for generations to come. The study of retrograde planets opens up profound implications not only for planetary science but also for the search for extraterrestrial life and the broader understanding of cosmic evolution. These unusual worlds challenge our assumptions about planetary formation, revealing that the universe is far more dynamic and chaotic than we once believed. Instead of being rare anomalies, retrograde planets may be a common outcome of gravitational interactions, migration processes, and cosmic collisions. As we refine our techniques for detecting and studying exoplanets, astronomers continue to uncover evidence that our current models of planetary system formation may need revision. Retrograde motion contradicts the traditional view that planets form in a neat, orderly fashion within a protoplanetary disk, aligning with the spin of their host star. Instead, the existence of retrograde planets suggests that many planetary systems undergo significant disturbances, leading to wildly different configurations than those seen in our solar system. One of the most intriguing questions surrounding retrograde planets is whether their unique orbits influence their internal structure and atmospheric conditions. For example, does a retrograde planet experience different levels of tidal heating compared to a prograde planet? Tidal forces, caused by the gravitational interactions between a planet and its star, can generate heat within a planet's interior, influencing volcanic activity, plate tectonics, and even the presence of liquid water. If retrograde planets experience stronger or weaker tidal effects, it could have significant implications for their geophysical evolution. Additionally, a planet's retrograde motion may impact its atmospheric dynamics in ways we have yet to fully understand. On Earth, the Coriolis effect, caused by the planet's rotation, plays a crucial role in shaping weather patterns, ocean currents, and wind systems. On a retrograde planet, the reversal of rotation might lead to drastically different climate systems. Stronger jet streams, unusual storm formations, or unique atmospheric circulation patterns could emerge, creating environmental conditions unlike anything we see in the solar system. There's also the possibility that retrograde planets experience extreme seasonal variations if their orbits are highly tilted or eccentric. In our solar system, Uranus, which has an extreme axial tilt, experiences extreme seasonal changes, with each pole alternately facing the sun for extended periods. If a retrograde exoplanet has a similar tilt, it could undergo long, harsh seasons that might influence its potential for habitability. Another question that arises is whether moons orbiting retrograde planets would also be affected by their host planet's unusual motion. If a retrograde planet has moons, do they orbit in the same direction as the planet's rotation, or do they follow more chaotic paths? Could retrograde planets harbor exomoons that are themselves in retrograde orbits? If so, how would that impact their stability over time? Some scientists have speculated that exomoons could be excellent candidates for life, particularly if they orbit within the habitable zone of a stable host planet. One of the most fascinating aspects of retrograde planets is the possibility that some of them may have originated as rogue planets, planets that formed in isolation or were ejected from their original star systems. If a rogue planet were later captured by a new star, its orbit might not align with the new system's natural rotation, resulting in a retrograde motion. This raises the possibility that some retrograde planets are not native to their current star systems, but are interstellar wanderers that found a new home through gravitational interactions. The existence of retrograde planets also has implications for planetary system stability. In many cases, when a planet moves in the opposite direction of its star's rotation, it can lead to increased gravitational disturbances, potentially affecting other planets in the system. Could retrograde planets be responsible for ejecting other planets or disrupting the formation of smaller rocky worlds? If so, this could mean that systems with retrograde planets are less likely to have stable, Earth-like planets in their habitable zones. Despite these challenges, the mere existence of retrograde planets demonstrates the incredible diversity of planetary systems across the galaxy. It forces astronomers to reconsider long-standing assumptions and explore new models of planetary evolution. The more we learn about these worlds, the more we realize that our own solar system may be just one of countless variations in an endless cosmic experiment. As new missions and observatories come online, we will gain even more insight into these mysterious planets. The James Webb Space Telescope has already begun studying the atmospheres of exoplanets in unprecedented detail, and future missions like the Habitable Worlds Observatory will push our understanding even further. By analyzing the chemical composition of retrograde planets, we may uncover clues about their formation history, migration paths, and even their potential for supporting life. Looking ahead, the next great challenge will be to determine just how common retrograde planets are. Are they rare exceptions, or are they a significant fraction of all exoplanets? To answer this question, astronomers will need to conduct large-scale surveys of exoplanetary systems, using both transit observations and radial velocity measurements to determine orbital orientations. If retrograde planets turn out to be widespread, it could revolutionize our understanding of planetary formation and the chaotic nature of young star systems. Ultimately, the study of retrograde planets reminds us that the universe is far stranger and more complex than we ever imagined. It challenges our assumptions, forces us to rethink established theories, and opens the door to new discoveries that could reshape our view of the cosmos. With every new retrograde planet we find, we take another step toward understanding the true nature of planetary systems, and perhaps, in the process, we move closer to answering one of the greatest questions of all: what else is out there, waiting to be discovered? The search for retrograde planets is more than just an academic curiosity. It has profound implications for the way we understand planetary formation, system stability, and even the likelihood of life elsewhere in the universe. As technology improves, we are no longer limited to detecting large gas giants with unusual orbits. We are beginning to uncover a much wider variety of exoplanets, some of which could challenge the very foundations of planetary science. One of the key questions that astronomers hope to answer is whether retrograde planets are more likely to be gas giants, or if smaller, rocky worlds can also form in these unusual orbits. So far, most of the confirmed retrograde exoplanets have been large, Jupiter-like planets, likely because these are easier to detect using current methods. However, as observation techniques improve, we may begin to find smaller, potentially habitable planets with retrograde motion. If rocky planets can exist in retrograde orbits, it raises a fascinating question about habitability. Could a world like Earth, but rotating in the opposite direction of its host star's spin, still support life? Theoretically, such a planet could have stable conditions for life as long as it remains within the habitable zone of its star. However, retrograde motion might introduce new atmospheric and climatic patterns, potentially leading to extreme weather or even unpredictable seasonal changes. One hypothesis suggests that a retrograde Earth-like planet might experience stronger or weaker magnetic field effects, depending on how its internal dynamo interacts with the reversed orbital motion. This could influence the planet's ability to protect itself from stellar radiation, which is a crucial factor for habitability. If the magnetic field is weaker, life may be less likely to develop due to higher radiation exposure. On the other hand, if the reverse motion somehow enhances magnetic field generation, it could create an even more protective shield than Earth's, potentially increasing the chances for complex life to emerge. Another question concerns the role of moons in retrograde planetary systems. In our solar system, most moons orbit their planets in the same direction as the planet's rotations, but there are exceptions, such as Neptune's moon Triton, which moves in a retrograde orbit. Triton is believed to be a captured object, possibly from the Kuiper Belt, rather than a moon that formed alongside Neptune. If retrograde exoplanets also have captured moons, this could indicate a history of gravitational disruptions, possibly involving close encounters with other planets or even interstellar objects. The presence of retrograde planets also challenges conventional ideas about planetary system stability. Traditionally, it was assumed that planetary systems form in a relatively stable manner, with all planets and their stars rotating in the same direction due to the angular momentum of the original protoplanetary disk. However, the discovery of multiple retrograde planets suggests that disruptions, whether from planetary migration, interstellar encounters, or other chaotic events, are far more common than previously believed. One possibility is that retrograde planets may be more common in crowded star systems, where gravitational interactions between multiple large planets frequently disrupt the orbits of smaller worlds. In such environments, planets could be thrown into highly inclined or retrograde orbits, or even ejected entirely from their systems. This idea is supported by observations of exoplanetary systems where multiple gas giants exist in close proximity, often with highly eccentric orbits. It's also worth considering the role of binary star systems in the formation of retrograde planets. Some astronomers have speculated that planets orbiting one star in a binary system might be more likely to end up in retrograde orbits due to complex gravitational interactions with the companion star. In such cases, a planet could start in a normal orbit but gradually be pulled into a retrograde path over millions of years as it responds to the combined gravitational influences of both stars. Interestingly, this could mean that planets in binary star systems are more likely to have unusual orbits than those in single-star systems like our own. If retrograde planets are indeed more common in binary systems, it could help explain why they seem to be rarer than expected. Our own solar system may simply be an outlier in terms of its stability. Another intriguing question is whether retrograde planets are more likely to harbor exotic forms of life. If a planet's reverse motion affects its climate and atmospheric circulation in unexpected ways, it could lead to the development of unique ecosystems, completely unlike anything found on Earth. Life, if it exists on such a world, may have adapted to conditions that are vastly different from those in our own biosphere. For example, if a retrograde planet experiences unusual day-night cycles due to its reversed orbit, life forms might have evolved to take advantage of extended periods of darkness or extreme temperature fluctuations. Some astrobiologists have speculated that life on such worlds could be subterranean, thriving in environments protected from surface conditions. Others have proposed that atmospheric life, similar to the floating organisms hypothesized to exist in Venus's clouds, might be more common in retrograde planetary systems. Beyond habitability, the study of retrograde planets also offers insight into the broader history of the galaxy itself. If these worlds are the result of planetary migration, then their presence provides evidence of the violent and chaotic processes that shaped the Milky Way over billions of years. By studying these planets, we are essentially looking back in time, uncovering clues about how planetary systems evolve and change over cosmic timescales. There's also the possibility that some retrograde planets originated outside their current star systems. If an interstellar object like Oumuamua, a mysterious, elongated object that passed through our solar system in 2017, were captured by a star's gravity, it could eventually settle into a retrograde orbit around its new host. If large planets can be captured in this way, it could mean that some retrograde exoplanets are actually former rogue planets, having spent part of their existence drifting through the void between stars. This raises an even more provocative question. Could life exist on a planet that has spent time as a rogue world before being captured by a star? If a planet with a subsurface ocean was ejected from its original system and then later caught in the gravity of a new star, could life have survived the transition? If so, retrograde planets could hold the key to understanding how life might spread between star systems, potentially supporting the idea of panspermia, the hypothesis that life can be transferred between planets and even across interstellar distances. As we continue to discover more exoplanets, the significance of retrograde worlds will only grow. They challenge our models, force us to rethink how planetary systems form, and may even offer new clues about the potential for life in the universe. The study of retrograde planets is still in its early stages, but each new discovery brings us closer to understanding the full complexity of planetary evolution. The universe, it seems, is far stranger than we ever imagined. Instead of neat, orderly planetary systems, we are beginning to see a picture of chaos, where worlds collide, migrate, and sometimes even reverse their direction entirely. As astronomers push the boundaries of what we know, one thing is certain: retrograde planets are just the beginning of a much deeper mystery waiting to be unraveled. The existence of retrograde planets also raises profound questions about the long-term stability of planetary systems. If a planet's orbit can be flipped, what does that say about the gravitational balance of its star system? Traditional models of planetary evolution assume that once planets form, their orbits remain relatively stable over billions of years unless disrupted by a catastrophic event. Yet, the presence of retrograde planets suggests that disruptions may be more common than previously believed. One possible explanation is that planetary systems experience periodic instability, during which planets undergo drastic changes in their orbits before eventually settling into new, stable configurations. This idea is supported by computer simulations that show how massive planets can influence the movement of smaller worlds, leading to orbital shifts over time. In some cases, a planet's orbit might even flip multiple times before reaching its final state. This means that a planet we observe today in a retrograde orbit may not have always been that way. If we could observe these systems over millions or billions of years, we might see planets transitioning from prograde to retrograde motion and vice versa. This suggests that planetary systems are far more dynamic than we once thought, constantly reshaping themselves as gravitational interactions play out over immense timescales. But what about the consequences of such orbital changes? A planet that shifts from a normal orbit to a retrograde one might experience extreme internal stress due to gravitational forces acting in unexpected ways. This stress could lead to increased volcanic activity, shifts in tectonic plates, or even changes in atmospheric composition. If the planet has a thick atmosphere, such disruptions could trigger long-term climate changes, potentially making the world more or less hospitable to life. Another question that arises is whether moons can exist in stable orbits around retrograde planets. In our solar system, most moons orbit in the same direction as their host planet's rotation, but there are exceptions like Neptune's moon Triton, which is thought to be a captured object. If a retrograde planet has moons, their orbital behavior could provide clues about the planet's history. For example, if its moons also move in retrograde orbits, it could indicate that they formed alongside the planet, rather than being captured later. In some cases, the gravitational effects of a retrograde planet's motion could make it difficult for moons to remain in stable orbits. Over time, tidal forces might cause the moons to spiral inward and crash into the planet, or be ejected from the system entirely. This means that retrograde planets might have fewer moons than their prograde counterparts, or that their moons might be relatively young, having formed after the planet settled into its unusual orbit. Observations of retrograde planets also provide insights into the broader architecture of planetary systems. If a star has multiple planets, and one of them is in a retrograde orbit, it suggests that the system has undergone significant gravitational interactions in the past. This could be evidence of planetary migration, where massive planets move inward or outward from their original positions, disturbing other planets in the process. One particularly intriguing possibility is that retrograde planets could serve as markers for hidden planetary companions. If a planet's orbit has been flipped, it likely means that it interacted with another large body at some point. If we can identify a retrograde planet, it might lead us to the discovery of additional planets in the system, potentially including worlds that are currently undetectable using existing methods. There's also the question of how common retrograde planets really are. So far, most of the retrograde exoplanets we've discovered are hot Jupiters, massive gas giants that orbit very close to their stars. This is likely due to observational bias, as these planets are easier to detect using current techniques. However, this raises an important question. Are retrograde planets more common among certain types of planets? Or do we just happen to find more retrograde hot Jupiters because they're easier to spot? If retrograde motion is more common among gas giants, it could suggest that the process responsible for flipping orbits is more effective for massive planets. One possibility is that smaller, rocky planets are less likely to survive the kinds of interactions that lead to retrograde orbits. If a large gas giant undergoes a gravitational disruption, it might have enough mass to stabilize in a new orbit, whereas a smaller planet might be ejected from the system entirely. However, if future observations reveal retrograde motion in smaller planets, it would indicate that the mechanisms driving these orbit reversals are not limited to massive worlds. This could mean that retrograde terrestrial planets exist, some of which may even be located within their stars' habitable zones. If such planets exist, they could present some of the most intriguing targets for future studies of planetary habitability. Another factor to consider is how a planet's retrograde motion might affect its climate and weather patterns. On Earth, the planet's rotation and orbit influence ocean currents, atmospheric circulation, and even seasonal changes. If Earth were in a retrograde orbit, its weather systems could behave very differently, potentially affecting everything from storm patterns to temperature distribution. For a retrograde exoplanet, the combination of an unusual orbital path and a reverse rotational direction could lead to entirely unique climate systems. If the planet's day-night cycle is also affected by its reverse motion, it could result in extreme seasonal variations, with some regions experiencing prolonged periods of daylight or darkness. These conditions could have profound implications for any potential life forms, requiring them to adapt to unpredictable environmental shifts. One of the biggest challenges in studying retrograde planets is understanding their long-term evolution. If a planet's orbit has been flipped once, could it happen again? Some models suggest that once a planet has settled into a stable retrograde orbit, it's unlikely to change unless another significant gravitational interaction occurs. However, if a system has already experienced enough disruption to create a retrograde planet, it's possible that additional changes could occur in the future. In extreme cases, a planet might transition from prograde to retrograde motion multiple times over its lifetime, with each shift altering its climate, atmospheric composition, and potential for life. This idea leads to an even more radical question. Could a planet in a stable retrograde orbit eventually return to a prograde orbit through a series of complex gravitational interactions? If so, it would mean that planetary orbits are even more fluid and dynamic than we currently believe. The study of retrograde planets is still in its early stages, but the discoveries made so far suggest that they may be more common than we once thought. As new telescopes and observational techniques come online, we are likely to find even more of these mysterious worlds, each one providing new clues about the chaotic processes that shape planetary systems. Ultimately, retrograde planets challenge many of our assumptions about how the universe works. They demonstrate that planetary systems are not always orderly, that gravity can produce unexpected results, and that the story of a planet's formation may be far more complex than a simple, linear progression. The existence of these worlds forces us to expand our understanding of planetary dynamics, to rethink how planets interact with their environments, and to consider new possibilities for what kinds of worlds might exist beyond our solar system. As we continue to explore the universe, one thing is clear: retrograde planets are not anomalies or exceptions, but rather key pieces of a much larger puzzle. Each new discovery brings us closer to unlocking the full story of how planets form, evolve, and sometimes defy the very laws of physics that govern the cosmos. The more we uncover about retrograde planets, the more we realize how much we still don't know about planetary formation, migration, and system-wide interactions. These mysterious worlds challenge the traditional models of planetary behavior and force us to reconsider the fundamental principles of celestial mechanics. What we once thought was a straightforward process, planets forming from a protoplanetary disk and settling into stable, predictable orbits, now appears to be far more chaotic and dynamic. One of the most significant implications of retrograde planets is their effect on exoplanet habitability studies. The search for life beyond Earth largely focuses on planets located within the habitable zone, the region around a star where liquid water can exist on a planet's surface. However, the discovery of retrograde planets suggests that habitability may be influenced by factors we have yet to fully understand. For instance, a retrograde orbit could impact the length of a planet's seasons and the stability of its climate. In some cases, the gravitational disturbances that flip the planet's orbit might also have stripped away its atmosphere, making it inhospitable to life as we know it. On the other hand, if a retrograde planet managed to retain a thick atmosphere, the unusual interplay of solar radiation and planetary rotation could create unique conditions, perhaps even climates that are more stable than those of traditionally orbiting planets. Another intriguing aspect of retrograde planets is their potential link to planetary system architecture. In our solar system, the planets follow relatively uniform, prograde orbits, leading to the assumption that this is the norm. However, the presence of retrograde exoplanets suggests that many planetary systems may not be as orderly as our own. If chaotic gravitational interactions are common in exoplanetary systems, then our solar system may actually be the exception rather than the rule. This raises important questions about planetary system evolution. Did our solar system simply avoid the gravitational disruptions that create retrograde planets, or was it once home to such anomalies that were later ejected or destroyed? Could a rogue planet have once passed through our system, altering orbits before being flung into interstellar space? The discovery of retrograde exoplanets opens up the possibility that our own cosmic backyard might have experienced far more turbulence in the past than we currently realize. One of the most perplexing questions surrounding retrograde planets is whether their unusual motion affects the likelihood of life. Most of our understanding of planetary habitability is based on Earth's prograde orbit and rotation, but a retrograde world would experience drastically different solar exposure patterns. If the planet's rotation is also reversed, it could mean that the sun rises in the west and sets in the east, fundamentally altering atmospheric dynamics, ocean currents, and even weather patterns. A planet's magnetic field, which is crucial for protecting it from harmful stellar radiation, might also be affected by its orbital orientation. If a planet experienced extreme gravitational interactions that flipped its orbit, those same forces might have disrupted its internal dynamo, the mechanism that generates a magnetic field. This could leave a retrograde planet more vulnerable to solar winds, potentially stripping away its atmosphere over time. Conversely, if a retrograde planet retains a strong magnetic field, it might develop unique atmospheric conditions that allow for unexpected forms of habitability. For example, intense auroras and electromagnetic interactions could influence cloud formation and temperature regulation, creating climate patterns that we have yet to consider. One of the biggest challenges in studying retrograde planets is determining how many exist and how they vary in size, composition, and location. Currently, most of the confirmed retrograde planets are gas giants, largely because they are easier to detect using the radial velocity and transit methods. But if we are able to detect retrograde terrestrial planets in the future, it could drastically reshape our understanding of planetary formation. Could an Earth-like world exist in a retrograde orbit? If so, how would life adapt to such an environment? Would it evolve differently due to the altered day-night cycle and unusual climate patterns? If microbial life can survive in extreme conditions on Earth, such as deep-sea hydrothermal vents or the frozen tundras of Antarctica, then perhaps life could also adapt to the strange conditions of a retrograde planet. Another major factor to consider is the potential for retrograde planets to host moons. A moon in a prograde orbit around a retrograde planet would experience highly unusual gravitational interactions. Its tidal forces could be vastly different from those of Earth's moon, possibly leading to extreme volcanic activity or unpredictable orbital variations. If a retrograde planet has captured a moon, that Moon's history could provide valuable clues about the planet's past interactions. In some cases, a captured moon might not remain in a stable orbit for long. The conflicting gravitational forces could cause it to spiral inward, leading to a cataclysmic collision, or it could be ejected from the system altogether. This means that retrograde planets might have a much higher rate of moon loss compared to their prograde counterparts. If future observations confirm this, it would further reinforce the idea that these planets exist in highly volatile environments. The study of retrograde planets also ties into the broader question of planetary system formation across the galaxy. Are these backward orbiting worlds common, or are they rare anomalies? If they are widespread, what does that tell us about the formation and evolution of exoplanetary systems? One possibility is that retrograde planets could be remnants of violent pasts, worlds that survived cosmic upheavals that destroyed or ejected other planets. If so, studying them could provide insights into the frequency and scale of interplanetary collisions, gravitational disruptions, and even rogue planet interactions. The role of rogue planets in shaping retrograde orbits cannot be ignored. A rogue planet passing through a system could exert enough gravitational influence to flip the orbit of an existing planet, permanently altering its trajectory. If rogue planets are more common than previously thought, they could be responsible for many of the strange planetary configurations we observe today. This idea also raises a fascinating possibility. Could a retrograde planet one day become a rogue planet? If continued gravitational interactions destabilize its orbit, it might eventually be ejected from its star system, wandering the galaxy as a lone, frozen world. Such a transition would be nearly impossible to observe in real time, but computer models might help us determine how often this occurs. Retrograde planets also challenge our understanding of planetary rings. In our solar system, rings tend to form around massive planets with strong gravitational fields, such as Saturn. However, if a retrograde planet were to have rings, their behavior might be very different from what we observe in our own system. Depending on the planet's rotation and orbital orientation, the rings could be tilted at extreme angles or even display irregular patterns that defy expectations. The study of these unusual worlds is still in its infancy, and many questions remain unanswered. Future space telescopes, such as the James Webb Space Telescope and its successors, will be crucial in identifying and analyzing retrograde planets in greater detail. By studying their atmospheres, compositions, and interactions with their host stars, scientists hope to unlock the secrets of how these mysterious planets came to be. One thing is certain: retrograde planets are not mere curiosities. They represent a fundamental challenge to our understanding of planetary science, pushing the boundaries of what we thought was possible in the universe. Each new discovery brings us closer to unraveling the mysteries of these backward-moving worlds, revealing the incredible complexity of the cosmos. As our technology advances and our ability to detect and study exoplanets improves, we will likely discover even more retrograde worlds, each with its own unique story to tell. Whether they are the survivors of ancient cataclysms, the products of extreme gravitational interactions, or the result of unseen cosmic forces, one thing is clear: the universe is far stranger and more dynamic than we ever imagined. The discovery of retrograde planets is not just a curiosity, it is a direct challenge to the way we understand planetary formation and the evolution of star systems. Each time we uncover a new exoplanet with an unexpected orbit, we are forced to refine our theories and explore possibilities that once seemed unlikely. These worlds, which move against the natural spin of their stars, exist in defiance of our most basic models of celestial mechanics, and yet, they are undeniably real. Their very existence suggests that planetary systems across the universe are far more chaotic and unpredictable than we ever imagined. One of the biggest questions surrounding retrograde planets is whether they are as common as prograde ones. Because our detection methods are still relatively limited, we may be overlooking many such planets simply because we lack the necessary technology to observe them properly. The more we refine our techniques, whether through direct imaging, transit observations, or radial velocity measurements, the more likely we are to find additional examples of retrograde planets, potentially even small, Earth-like ones. The implications of finding a retrograde Earth-like planet would be profound. Would such a world have a stable climate? Would its weather patterns be dramatically different from those of Earth? If life evolved there, would it be fundamentally altered by the unusual orbital conditions? These are questions we cannot yet answer, but they are exactly the kinds of mysteries that make astronomy one of the most exciting fields of science. Another aspect of retrograde planets that deserves further exploration is the possibility that they could be evidence of unseen forces at play in planetary systems. Could dark matter influence planetary orbits in ways we have not yet considered? Could some retrograde planets be the remnants of interstellar objects that were captured by a star's gravitational pull? There is still so much we do not know about how celestial bodies interact, and retrograde planets could provide crucial clues to solving some of the biggest unanswered questions in astrophysics. Additionally, the study of retrograde planets ties into broader questions about planetary migration. Many planetary systems appear to be highly dynamic, with planets shifting positions over time due to gravitational interactions. If a planet can move inward or outward from its star, is it also possible for its orbit to be flipped entirely? If so, what kind of energy transfer would be required to make such a dramatic change possible? Some scientists believe that planetary migrations are relatively common, with planets being pushed and pulled by gravitational forces as they interact with their neighbors. This is one possible explanation for how some retrograde planets came to exist. They might have started as normal, prograde planets but were forced into their current orbits after colliding with other celestial bodies or being influenced by massive planets in their system. Understanding the mechanics of these interactions is not just an academic exercise. It could also help us predict the long-term future of our own solar system. If planetary orbits can be drastically altered over time, could Earth's orbit change in the distant future? Could an encounter with a rogue planet or an interstellar object disrupt the delicate balance that keeps our planet in the habitable zone? These are possibilities that astronomers must consider as they continue to study the evolution of planetary systems. Beyond the theoretical implications, retrograde planets also present a fascinating puzzle when it comes to planetary atmospheres and surface conditions. If a planet orbits in the opposite direction of its star's rotation, how does that affect its atmospheric circulation? On Earth, weather patterns are largely driven by the Coriolis effect, which is influenced by the planet's rotation. If an exoplanet rotates in one direction but orbits in another, how would that impact winds, storms, and temperature distribution? One possibility is that retrograde planets could have much more extreme weather than their prograde counterparts. The interaction between stellar radiation and a reverse planetary rotation could create superstorms, permanent high-pressure systems, or even unique climate zones that do not exist on Earth. If an exoplanet has a thick atmosphere, such as a gas giant, the effects could be even more dramatic, with intense jet streams and temperature variations unlike anything we have observed before. Another factor to consider is whether retrograde planets could have unusual day-night cycles. On Earth, the length of a day is determined by the planet's rotation, but if an exoplanet's rotation and orbit are misaligned, its days and nights could be significantly different from what we experience. Some retrograde planets might have extremely long days or chaotic seasonal cycles, which could have significant implications for potential life forms. If an Earth-sized retrograde planet were to exist in a habitable zone, life there would have to adapt to these strange conditions. Would plants still use photosynthesis in the same way? Would animals develop entirely different sleep cycles or behavioral patterns? Could intelligent life evolve under such conditions, and if so, would their perception of time and celestial motion be fundamentally different from ours? One of the most exciting aspects of studying retrograde planets is the potential for future missions to directly observe them. As space telescopes become more advanced, we may be able to analyze the atmospheres of these worlds in detail, searching for signs of water, oxygen, or even biological activity. If a retrograde planet were found to have an Earth-like atmosphere, it would challenge many of our assumptions about the conditions necessary for life to thrive. In the coming decades, missions such as the James Webb Space Telescope and future generations of observatories will play a crucial role in uncovering the secrets of these strange planets. By studying their compositions, movements, and atmospheres, we may be able to determine whether they are the result of natural planetary evolution or the remnants of ancient cosmic catastrophes. The existence of retrograde planets is a reminder that the universe is far more complex than we once believed. For every rule we think we understand, there is an exception that forces us to look deeper, question our assumptions, and refine our models. These planets are not just anomalies. They are pieces of a much larger puzzle, one that will take generations to fully unravel. As our technology improves and our ability to observe distant worlds becomes more sophisticated, we will undoubtedly discover even more planets that defy expectations. Some may orbit backward, others may have highly eccentric paths, and still others may exhibit properties we have never even considered. Each new discovery will bring us closer to understanding the incredible diversity of planetary systems in the cosmos. Ultimately, the study of retrograde planets is about more than just understanding how they came to be. It is about expanding our knowledge of the universe and embracing the unknown. Every time we look at the stars, we are reminded that the cosmos is filled with mysteries waiting to be solved, and retrograde planets are among the most intriguing of them all. The question now is not whether retrograde planets exist. We know they do. The real question is, how many are out there, and what secrets do they hold? The search for answers continues, and with each new discovery, we take another step closer to unraveling one of the greatest mysteries of space. The implications of retrograde planets extend beyond just their formation and dynamics. They also challenge our understanding of planetary system evolution and stability. One of the biggest questions facing astronomers is whether these worlds can remain in their unusual orbits indefinitely or if they are doomed to eventual destruction. The gravitational interactions that likely cause these planets to flip their orbits in the first place could also make them unstable over long periods. Some retrograde planets may be on borrowed time, their strange paths setting them up for future collisions with other celestial bodies or for being flung out of their systems entirely. This leads to another fascinating possibility. Could some of the rogue planets wandering the galaxy be former retrograde planets that were ejected from their home systems? Rogue planets, planets that float freely through space without orbiting any star, are believed to be incredibly common, possibly even outnumbering the stars in the Milky Way. If retrograde planets are more likely to experience unstable gravitational interactions, they might have a higher chance of being expelled into interstellar space. If so, the population of rogue planets could be partially made up of worlds that once defied the rules of their home systems, only to be cast out into the cold darkness of the cosmos. This idea raises another question: what happens to a planet that is ejected from its system? Without the warmth of a star, a rogue planet would be a frozen wasteland, yet recent studies suggest that some of these planets could still retain internal heat for billions of years. If a rogue planet had a thick atmosphere or even an underground ocean, it might still be able to support some form of life, despite drifting alone through space. Could some former retrograde planets now be harboring hidden ecosystems beneath thick layers of ice? If so, they could be among the most isolated and mysterious habitable worlds in the universe. The role of retrograde planets in planetary system evolution is also tied to the fate of their host stars. In many cases, these planets orbit close to their stars, sometimes even within the range where tidal forces become significant. A retrograde planet that gets too close to its star may eventually experience tidal disruption, where the immense gravitational pull of the star stretches and deforms the planet, possibly leading to its destruction. This could result in the formation of planetary debris disks, rings of material left behind after a planet is torn apart. Observations of distant stars have already revealed such debris disks, some of which may be the remnants of destroyed retrograde planets. These disks, made up of rocky fragments and dust, could provide valuable clues about the history of planetary systems and the violent events that shaped them. By studying these remnants, astronomers might be able to reconstruct the past lives of planets that no longer exist, offering a unique window into the chaotic history of exoplanetary systems. Another possibility is that some retrograde planets could eventually spiral into their stars due to gravitational interactions. If this happens, the process could generate intense bursts of energy, creating observable signatures that astronomers might be able to detect. Some mysterious stellar flares or unusual outbursts could be the final moments of retrograde planets meeting their fiery demise. If we can identify such events, we may be able to witness, in real time, the destruction of a world that once moved against the current of its star's rotation. The study of retrograde planets also ties into the broader field of planetary system diversity. For decades, our understanding of planetary formation was based primarily on our own solar system. We assumed that most planetary systems would follow a similar pattern: rocky planets close to the star, gas giants farther out, all orbiting in the same direction as their star's rotation. However, as we have discovered more exoplanets, we have learned that planetary systems are far more diverse than we ever imagined. Retrograde planets are just one example of how nature refuses to conform to our expectations. In fact, some planetary systems appear to be so chaotic that they barely resemble our own at all. There are systems where gas giants orbit closer to their stars than Mercury does to the Sun, systems where planets follow elongated, highly eccentric orbits, and even systems where planets appear to orbit at extreme angles relative to the plane of their star's rotation. Retrograde planets are part of this broader picture, showing us that planetary formation is not a simple, orderly process but rather a chaotic, dynamic dance influenced by countless variables. As we continue to refine our methods of detecting and studying exoplanets, we will undoubtedly discover even more strange and unexpected worlds. Future space telescopes, such as those designed to directly image exoplanets, may allow us to study retrograde planets in greater detail than ever before. By analyzing their atmospheres, compositions, and thermal emissions, we could learn more about their histories and the forces that shape them. One of the most exciting prospects for future research is the potential to identify biosignatures on retrograde planets. If an Earth-like retrograde planet exists in a habitable zone, it could host life, even under its unusual conditions. The detection of atmospheric gases such as oxygen, methane, or carbon dioxide in the right ratios could provide strong evidence of biological activity. If we were to discover life on a retrograde planet, it would challenge many of our assumptions about habitability and the conditions necessary for life to thrive. The implications of such a discovery would be profound. If life can exist on a planet with an orbit that defies conventional expectations, it suggests that life may be far more adaptable than we previously thought. This would increase the chances of finding life elsewhere in the universe, even on worlds that seem drastically different from our own. It would also raise fascinating questions about how evolution might unfold in environments that experience extreme variations in climate, seasons, and day-night cycles. The study of retrograde planets is about more than just understanding the mechanics of planetary motion. It is about expanding the boundaries of what we believe is possible in the universe. These strange, backward-orbiting worlds remind us that the cosmos is full of surprises, and that for every rule we think we understand, there is an exception waiting to be discovered. As we look to the future, it is clear that the search for retrograde planets is far from over. With each new observation, we gain a deeper understanding of how planets form, evolve, and interact with their environments. The mysteries of these worlds will continue to captivate astronomers for years to come, and with every new discovery, we come one step closer to unraveling the true complexity of the universe. Ultimately, the existence of retrograde planets is a testament to the sheer unpredictability of the cosmos. They are a reminder that the universe does not always follow the patterns we expect, and that sometimes, the most fascinating discoveries come from the places where reality defies our assumptions. With every new telescope we launch and every new exoplanet we study, we push the boundaries of human knowledge further into the unknown. Retrograde planets are just one piece of the puzzle, but they are an important one, proof that the universe is far more diverse, chaotic, and awe-inspiring than we ever dared to imagine. And so, the search continues. What other strange and unexpected worlds are waiting to be discovered? What new mysteries will we uncover as we explore the depths of space? The answers are out there, hidden among the stars, waiting for us to find them. The search for retrograde planets is far from over, and as our technology improves, we will uncover even more of these strange worlds. Future space missions, such as the James Webb Space Telescope, JWST, and upcoming next-generation observatories, will allow us to study exoplanets in unprecedented detail. With these powerful instruments, astronomers will be able to analyze the atmospheres of retrograde planets, determining their chemical compositions and searching for possible signs of life. One of the biggest questions surrounding retrograde planets is how their unusual orbits affect their climate and habitability. For Earth-like planets in retrograde orbits, the interaction between their rotation and their star's movement could create extreme weather patterns. A planet that rotates opposite to its orbit might experience bizarre day-night cycles, with the sun appearing to rise in the west and set in the east. Depending on the speed of its rotation, it could have dramatically different climate conditions compared to planets with more conventional orbits. Some retrograde planets might even be tidally locked, meaning that one side always faces their star while the other remains in perpetual darkness. This could create extreme temperature differences, with one hemisphere experiencing scorching heat and the other being frozen in eternal night. However, if these planets have thick atmospheres, winds and ocean currents could redistribute heat, potentially allowing for a habitable zone somewhere in between. If life exists on such a planet, it might be adapted to the unique challenges of living in an environment with such extreme contrasts. Another factor that makes retrograde planets interesting is their potential for hosting moons. The gravitational interactions that lead to a planet's retrograde motion might also affect its ability to capture or retain moons. Some models suggest that retrograde planets may have a harder time keeping stable moons due to the chaotic forces involved in their formation. However, if a retrograde planet does have moons, they could experience their own strange orbital effects. In our own solar system, some moons exhibit retrograde motion, such as Neptune's largest moon, Triton. Triton is thought to have been a captured object, likely originating from the Kuiper belt before being pulled into Neptune's orbit. This suggests that retrograde moons could be common around exoplanets, and if such a moon were to have an atmosphere or liquid water beneath its surface, it could be another candidate for habitability. There is also the possibility that some retrograde planets orbit binary star systems, where two stars orbit each other while a planet moves around them in an opposite direction. Such systems would create incredibly complex gravitational interactions, and the stability of a retrograde planet in such an environment would depend on the specific details of its orbit. If these planets can remain stable over long periods, they might experience dramatic variations in temperature and radiation as they move through the gravitational influence of both stars. One of the most intriguing aspects of retrograde planets is the possibility that their existence hints at unknown forces at work in the universe. If some retrograde planets form naturally in their current orbits rather than being disrupted by external interactions, it could suggest that planetary formation is even more diverse than we currently understand. There could be alternative mechanisms for planet formation that we have yet to discover, perhaps involving exotic processes that occur under extreme conditions or in environments unlike anything found in our solar system. Furthermore, the study of retrograde planets might help us better understand the fate of planetary systems over cosmic timescales. If retrograde motion is an indicator of past gravitational disturbances, then identifying patterns in the distribution of these planets could reveal broader trends in how planetary systems evolve. By analyzing their numbers, locations, and characteristics, astronomers may be able to reconstruct the histories of distant star systems, determining whether retrograde planets are more likely to exist in certain types of systems, or if they are distributed randomly throughout the galaxy. Another unexplored possibility is whether retrograde motion plays a role in the potential for intelligent life. If Earth had been a retrograde planet, would evolution have unfolded in the same way? Would the altered climate patterns and different day-night cycles have influenced the development of complex life? These are speculative questions, but they highlight how planetary motion could have profound implications for the emergence of life across the universe. As we move into the future, the search for retrograde planets will be driven by increasingly sophisticated methods of observation. The ability to directly image exoplanets, rather than just inferring their presence through indirect means, will provide new insights into their compositions, temperatures, and atmospheres. Upcoming missions like the Nancy Grace Roman Space Telescope and ground-based observatories equipped with advanced adaptive optics will refine our ability to detect and study these unique worlds. The next step in this journey could involve not just detecting retrograde planets, but actually sending probes to study them up close. While current technology does not yet allow us to travel to exoplanets, future generations may develop propulsion methods capable of reaching distant worlds. A probe sent to a retrograde planet could provide unparalleled data, revealing the surface conditions, atmospheric composition, and potential for habitability. Additionally, the search for retrograde planets could benefit from advances in artificial intelligence. Machine learning algorithms are already being used to sift through vast amounts of astronomical data, identifying potential exoplanet candidates with greater speed and accuracy than ever before. By training AI to recognize the unique signatures of retrograde motion, we may be able to discover more of these planets at an accelerated rate. Ultimately, retrograde planets are just one piece of the vast and complex puzzle of the universe. They challenge our assumptions, force us to reconsider what we thought we knew about planetary formation, and open the door to new and exciting questions. Whether they are the remnants of violent cosmic collisions, the products of gravitational chaos, or the result of unknown forces yet to be discovered, these worlds remind us that space is full of mysteries waiting to be solved. As we continue our exploration of the cosmos, retrograde planets will remain a key area of interest, offering valuable insights into the nature of planetary systems and the forces that shape them. Each new discovery brings us closer to understanding the fundamental principles that govern the universe, and with each new retrograde planet we find, we take another step toward unraveling the mysteries of the cosmos. The universe does not always follow the rules we expect, and that is what makes it so endlessly fascinating. The search for retrograde planets is not just about finding new worlds, it is about expanding our understanding of reality itself. The more we learn, the more we realize how much there is left to discover, and the journey to uncover the secrets of these strange, backward-moving planets is only just beginning. The deeper we dive into the study of retrograde planets, the more we uncover about the dynamic and often chaotic nature of planetary systems. These celestial oddities challenge the conventional wisdom that planets should form in alignment with their star's rotation, prompting astronomers to rethink the very foundations of planetary evolution. With every newly discovered retrograde planet, we gain insight into the forces that shape the cosmos, forces that are far more complex and unpredictable than we once imagined. One of the most compelling questions surrounding retrograde planets is their potential diversity. Are these worlds limited to gas giants, or could there be terrestrial retrograde planets, possibly even Earth-like worlds? So far, the majority of retrograde exoplanets discovered are hot Jupiters, massive gas giants that orbit their stars at close distances. This makes sense because current detection methods, such as the radial velocity technique and the transit method, are most effective at identifying large planets that exert a strong gravitational influence or pass in front of their stars. However, as detection techniques improve, we may begin to find smaller retrograde planets, including rocky worlds that could harbor liquid water and possibly life. If terrestrial retrograde planets exist, they could provide an entirely new perspective on planetary habitability. Would life on such a world evolve differently due to the reverse motion? Could a retrograde rotation create unique weather patterns, ocean currents, or geological activity? These are questions that scientists hope to answer in the coming decades. One of the most intriguing aspects of a retrograde world is how its reverse motion might affect its climate and atmospheric dynamics. On Earth, the Coriolis effect influences the direction of winds and ocean currents due to the planet's rotation. If Earth were to spin in the opposite direction while still orbiting the Sun in the same way, weather systems would likely behave in ways that are difficult to predict. Jet streams, trade winds, and even the distribution of rain and storms could be dramatically altered. For a planet with an extreme retrograde orbit, where both its rotation and orbital direction are reversed, the effects could be even more drastic. Days and nights might be longer or shorter depending on the planet's axial tilt and rotational speed. Some models suggest that a retrograde Earth might experience different seasonal shifts, as its orientation relative to the Sun would change in an unexpected way. The resulting climate could be alien compared to what we experience today, potentially affecting the evolution of life. Beyond individual planets, the study of retrograde motion has broader implications for understanding planetary system formation and stability. Some researchers believe that retrograde planets might be indicators of violent past events, such as close encounters with other stars or large-scale planetary migrations. If we find a higher frequency of retrograde planets in certain regions of the galaxy, it could suggest that these areas have undergone significant gravitational disturbances, possibly due to passing stars or interactions with nearby galactic structures. Another possibility is that retrograde planets are more common in multi-star systems, where complex gravitational forces could lead to unconventional orbital configurations. In binary or trinary star systems, planets can be influenced by the combined gravitational pull of multiple suns, leading to eccentric orbits that might include retrograde motion. Studying these systems could help us understand how multiple gravitational influences shape the fates of planets over billions of years. One particularly fascinating hypothesis is that some retrograde planets might be former rogue planets, worlds that were once free-floating in space before being captured by a star's gravity. If this is the case, these planets would have originated outside their current planetary system, raising questions about how many rogue planets exist in the universe, and whether they could serve as a means of spreading life from one system to another. The idea of planetary capture also ties into theories about panspermia, the concept that life might be transferred between planets, or even between star systems through meteorites or other celestial bodies. If a rogue planet harboring microbial life were to be captured into a retrograde orbit around a star, it could potentially introduce alien biology to an entirely new planetary system. This raises the possibility that some retrograde planets could be among the most biologically interesting worlds in the universe. To investigate these questions further, astronomers are working on refining methods for detecting and analyzing exoplanetary atmospheres. Spectroscopy allows us to break down the light from exoplanets and determine the chemical composition of their atmospheres, revealing the presence of elements like oxygen, carbon dioxide, and methane, gases that could hint at biological activity. If we find a retrograde planet with an atmosphere that contains biosignatures, it could challenge our understanding of how life emerges and survives in extreme environments. Looking ahead, future space telescopes will revolutionize our ability to study retrograde planets in greater detail. The European Space Agency's Plato mission, set to launch in the coming years, will focus on detecting Earth-like exoplanets, possibly including some in retrograde orbits. Additionally, next-generation observatories such as the proposed LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory, could provide high-resolution imaging of exoplanets, allowing scientists to directly observe atmospheric conditions and even surface features. The search for retrograde planets is also driving advancements in computational modeling. By simulating the gravitational interactions of exoplanetary systems, researchers can test different formation scenarios and determine which conditions are most likely to produce retrograde motion. These simulations help refine our theories about planetary migration, gravitational capture, and the long-term stability of unusual orbits. One of the most exciting aspects of studying retrograde planets is the potential for future interstellar missions. While current space travel is limited to our own solar system, concepts such as light sails, nuclear propulsion, and even warp drives are being explored as potential ways to reach distant exoplanets. If humanity develops the capability to travel beyond our solar system, one of the most intriguing targets for exploration could be a retrograde planet, where we might encounter conditions unlike anything we have seen before. Even if human space travel remains limited for the foreseeable future, robotic probes could be sent to study exoplanets up close. Concepts such as Breakthrough Starshot propose using laser-powered spacecraft to travel at a fraction of the speed of light, potentially reaching nearby star systems within a few decades. If such missions become a reality, retrograde planets could be among the first destinations chosen for detailed study. As our understanding of retrograde planets grows, we may find that these strange worlds are more than just anomalies. They may hold the key to unlocking deeper cosmic mysteries. Whether they reveal new insights about planetary formation, shed light on the potential for life in extreme conditions, or even challenge our assumptions about the laws of physics, retrograde planets remind us that the universe is full of surprises. The discovery of retrograde planets is a testament to the boundless complexity of space. Every time we think we have the answers, the cosmos presents us with new questions, pushing us to explore further, think deeper, and embrace the unknown. As we continue our search for these enigmatic worlds, one thing is certain: the universe is far more strange and wondrous than we ever imagined, and the journey to understand it is only just beginning. The mysteries surrounding retrograde planets extend beyond just their origins and potential habitability. They also challenge our fundamental understanding of planetary dynamics and raise questions about the long-term stability of these unusual orbits. One of the biggest unknowns in astrophysics is whether retrograde planets are destined to remain in their unconventional paths indefinitely, or if they will eventually be pulled into more conventional orbits, or even ejected from their star systems entirely. Gravity is the primary force shaping planetary systems, but it is not always predictable. While a prograde planet's orbit is generally more stable due to its alignment with the star's rotation, retrograde planets exist in a delicate gravitational balance. Over millions or even billions of years, small gravitational perturbations from other planets, passing stars, or the galactic tide could alter their orbits. In some cases, these perturbations could cause a retrograde planet to spiral inward toward its star, eventually being consumed. In others, the planet might be pushed further out, possibly becoming a rogue planet that drifts through interstellar space. The study of orbital mechanics suggests that some retrograde planets could be in metastable states, meaning they might remain in retrograde motion for long periods, but are ultimately destined for dramatic changes. If a retrograde planet shares a system with multiple other planets, gravitational interactions between them could create chaotic effects. This could lead to orbital shifts, planetary collisions, or even the ejection of one or more planets from the system. One of the most dramatic possibilities is that a retrograde planet could undergo a sudden orbital flip, switching from retrograde to prograde motion due to an extreme gravitational event. While this would be rare, it is theoretically possible if the planet experienced a close encounter with another massive object, such as a passing star or a wandering black hole. In such a scenario, the planet's orbit could be completely reshaped, altering its climate, geological activity, and possibly even its potential for hosting life. These extreme gravitational interactions highlight the importance of long-term simulations in astrophysics. Using powerful supercomputers, scientists can model the behavior of planetary systems over billions of years, testing different scenarios to understand how retrograde planets evolve. These simulations help researchers determine which conditions lead to stable retrograde orbits, and which ones result in planetary ejections or orbital transformations. One particularly intriguing question is whether retrograde planets could exist in habitable zones, the regions around stars where conditions might allow for liquid water. So far, most of the retrograde exoplanets discovered are hot Jupiters, which are unlikely to support life as we know it. However, if retrograde rocky planets exist in habitable zones, they could provide an entirely new perspective on the conditions necessary for life. If such planets do exist, they might experience unique day-night cycles due to their reverse motion. Depending on their rotation speed and axial tilt, some retrograde planets could have unusual climate patterns that differ significantly from those on Earth. This could affect atmospheric circulation, ocean currents, and even the potential for complex ecosystems to develop. Another intriguing possibility is that retrograde planets could play a role in planetary system evolution by influencing the orbits of other planets. If a massive retrograde planet exists in a system with smaller, prograde planets, its gravitational influence could cause orbital instabilities, potentially leading to planetary migrations or even collisions. This could help explain why some exoplanetary systems appear so different from our own, with planets in highly eccentric orbits or unexpected arrangements. The presence of retrograde planets might also be linked to the existence of exomoons, moons that orbit planets outside our solar system. If a retrograde planet has moons, their orbits could be even more complex, potentially leading to unusual tidal effects, extreme variations in surface conditions, and unpredictable seasonal changes. Some scientists speculate that retrograde planets might have captured exomoons from other parts of their system, leading to entirely new types of planetary-moon interactions. One of the most exciting future prospects for studying retrograde planets is the possibility of direct imaging. While current detection methods rely primarily on indirect techniques such as transit photometry and radial velocity measurements, future space telescopes could allow us to directly observe these planets. By capturing high-resolution images, scientists could analyze surface features, atmospheric composition, and even weather patterns in real time. In addition to direct imaging, advancements in spectroscopy will be critical for understanding the atmospheres of retrograde planets. By analyzing the light that passes through a planet's atmosphere, astronomers can identify chemical signatures that could indicate the presence of water, oxygen, or other key elements. If a retrograde planet is found to have an atmosphere rich in biosignatures, it could become a prime candidate for further study in the search for extraterrestrial life. The search for retrograde planets is also shedding light on the broader question of planetary diversity. As more exoplanets are discovered, it is becoming increasingly clear that our solar system is not necessarily a typical example of how planetary systems form. The presence of retrograde planets, hot Jupiters, super-Earths, and other unusual worlds suggests that planetary formation is a highly dynamic and often chaotic process, shaped by a wide range of factors that we are only beginning to understand. As we continue to explore the cosmos, retrograde planets serve as a reminder that the universe is full of surprises. Each new discovery challenges our assumptions and expands our understanding of how planets form, evolve, and interact with their environments. With the next generation of telescopes and space missions, we are on the brink of uncovering even more extraordinary worlds that defy expectations and force us to rethink what is possible in the vast and mysterious expanse of space. The study of retrograde planets is not just about understanding individual worlds. It is about unraveling the deeper mysteries of the universe itself. These planets offer clues about cosmic collisions, planetary migrations, and the intricate dance of gravity that shapes entire star systems. They challenge us to consider new possibilities about habitability, extraterrestrial life, and the fundamental laws governing planetary motion. As technology advances and our ability to study exoplanets improves, the discoveries we make about retrograde planets will continue to reshape our view of the cosmos. Perhaps one day, we will even send a probe, or a crewed mission, to explore one of these enigmatic worlds up close. Until then, the search for retrograde planets remains one of the most fascinating and rewarding frontiers in modern astronomy, offering endless opportunities for discovery and wonder. The implications of retrograde planets extend far beyond their orbits. These peculiar worlds challenge some of our deepest assumptions about how planetary systems form and evolve. The existence of these planets suggests that planetary migration is more common and chaotic than previously thought, potentially reshaping entire star systems in unpredictable ways. As we continue to uncover more of these anomalies, astronomers are forced to rethink their models of planet formation, reconsidering factors such as gravitational interactions, stellar influences, and the role of cosmic collisions in shaping planetary architecture. One of the most important aspects of studying retrograde planets is understanding their atmospheric composition. Since many of these worlds are hot Jupiters, their thick, gaseous atmospheres make them ideal candidates for spectroscopic analysis. By observing how light interacts with these atmospheres, astronomers can detect the presence of elements such as hydrogen, helium, water vapor, carbon dioxide, and even more complex organic molecules. If retrograde planets have unusual chemical compositions, this could provide further insight into how they formed and whether they originated within their current systems or were captured from interstellar space. The idea that some retrograde planets could be interstellar captures is an intriguing one. If a rogue planet were to drift into a star system and become gravitationally bound to a host star, it could settle into a retrograde orbit. This raises the possibility that some of these worlds might not have formed alongside their current stars at all but instead originated in entirely different parts of the galaxy. If this is the case, retrograde planets could serve as time capsules, carrying chemical signatures from distant star-forming regions and providing clues about the history of planetary formation beyond their host systems. Additionally, the study of retrograde planets could shed light on one of the greatest mysteries in astrophysics: the role of dark matter in planetary formation. While dark matter is not directly observable, its gravitational effects influence the motion of galaxies and galaxy clusters. Some scientists speculate that dark matter may also play a role in the formation and stability of planetary systems, potentially affecting the dynamics of retrograde planets in ways we do not yet fully understand. If future studies reveal patterns in the distribution or behavior of retrograde planets that cannot be explained by conventional physics, this could provide indirect evidence for dark matter's influence on planetary formation. The potential for life on retrograde planets remains one of the most fascinating questions in astrobiology. While most confirmed retrograde planets are gas giants, the possibility of retrograde rocky planets existing in habitable zones cannot be ruled out. If such planets do exist, their reverse motion could lead to unique environmental conditions, including unusual day-night cycles, extreme climate variations, and possibly even exotic weather patterns driven by atmospheric turbulence. The presence of liquid water, stable temperatures, and protective magnetic fields would all be crucial factors in determining whether life could emerge on these strange worlds. One of the most exciting upcoming tools for studying retrograde planets is the James Webb Space Telescope, JWST. With its powerful infrared capabilities, JWST is already revolutionizing our understanding of exoplanet atmospheres, allowing scientists to analyze the chemical makeup of distant worlds in unprecedented detail. If JWST detects biosignatures, such as oxygen, methane, or other light-related compounds, on a retrograde exoplanet, this could have profound implications for the search for extraterrestrial life. In the coming decades, next-generation telescopes such as the Extremely Large Telescope, ELT, and the Habitable Worlds Observatory, HWO, will further expand our ability to study exoplanets in detail. These instruments will be capable of directly imaging smaller, Earth-sized exoplanets, and analyzing their atmospheres with extreme precision. If any retrograde planets are found to have conditions suitable for life, these discoveries could redefine our understanding of habitability and planetary evolution. The study of retrograde planets also ties into the broader search for extraterrestrial intelligence, SETI. If advanced civilizations exist elsewhere in the galaxy, it is possible that some of them might inhabit or even intentionally settle on retrograde planets. The unique orbital dynamics of these worlds could make them prime locations for advanced engineering projects, such as Dyson spheres or other megastructures designed to harness stellar energy. If any unusual artificial signals are detected from retrograde planets, this could provide compelling evidence of intelligent extraterrestrial activity. Another important consideration is the impact of retrograde planets on planetary system stability. In systems with multiple planets, a retrograde world could act as a disruptor, altering the orbits of its neighbors and potentially triggering cascading gravitational effects. This could help explain why some exoplanetary systems appear so different from our own, with planets in eccentric orbits, strange alignments, or unexpected configurations. Understanding these dynamics could provide valuable insights into the long-term evolution of planetary systems and the factors that determine their stability. The presence of retrograde planets may also influence the formation of moons and rings. If a gas giant forms in a retrograde orbit, any moons it captures or forms could end up in similarly reversed orbits. This could lead to unique tidal interactions, affecting everything from volcanic activity to atmospheric retention. Studying retrograde exomoons could provide additional clues about how these planets formed and whether they host conditions suitable for life. As we continue to discover more exoplanets, it is likely that retrograde planets will become an increasingly common area of study. The sheer diversity of planetary systems challenges the notion that there is a standard way for planets to form. Each new discovery brings us closer to understanding the full range of possibilities in the universe, pushing the boundaries of what we consider normal or expected. Ultimately, the existence of retrograde planets is a testament to the incredible complexity of the cosmos. These worlds defy our expectations, challenge our theories, and force us to reconsider what we know about planetary formation, gravitational interactions, and even the potential for life beyond Earth. As we venture deeper into the study of exoplanets, the mysteries of retrograde worlds will continue to captivate astronomers and space enthusiasts alike, offering new opportunities for discovery and inspiring the next generation of space exploration. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.